So it's an honor for me to speak at this meeting in honor of Ahmed Zewail. I didn't know Zewail myself personally. I work in a very different area. But it's very clear from yesterday that not only was he a great scientist, but also a great human being. Originally, when I was invited to speak at this meeting, I thought I'd talk about four-stranded DNA structure, which is an area of research which both Antoine, our chair, and I work on. But then reading about Zewail's later work and also hearing the talk yesterday, I decided to change my subject and actually tell you about the resolution revolution in electron microscopy, in cryo-electron microscopy. As most of you will know, some of the later publications from Zewail were on 4D cryo-electron microscopy of proteins. And as he gives me the introduction to my talk, cryo-electron microscopy is a form of transmission electron microscopy that has been used to determine the 3D structure of biological specimens in the hydrated state with high resolution. So in this paper, they report the use of 4D cryo-electron microscopy to integrate in the fourth dimension, time, into this powerful technique. So from time-resolved diffraction of amyloid fibers, so this is a setup. You have amyloid fiber, you heat them up with a heating pulse, and then, of course, you have the electron beam, and you look at the diffraction fraction. From this, Zewail found that from time-resolution diffraction of amyloid fibers in thin layer of vitrified water at cryogenic temperatures, they were able to detect picometer movements of protein molecules on nanoscale, time scale. Again, from Zewail's one of his publications in Science, where he reviews the field, he says, from the historical perspective, which I also will go through, the progress in the field has been made over a century of development. Of course, first of all, with the discovery of the electron by J.J. Thomson, that it has a wave, and this laid the foundation then to build the first 2D electron microscopes in the 1930s. 3 decades later, 3D image reconstruction from a single projection, or I would say many projections, by the Rosier, Klug, and Crowther, and from Tilt series by Hart and others was achieved. So my link into this is that Aaron Klug was my PhD supervisor. So that's how but actually, curiously, when I worked with him, I mostly did crystallography. I've only really seriously done electron microscopy since I came here to NTU from Cambridge. So in my talk, I will tell you about how we use cryo-EM to determine the 3D structure of proteins. So no movement, but as you will see, we can actually, because we can collect huge data set, we can actually define different conformations of the same proteins. And I'll show you a couple of examples of work done here at NTU. And of course, to be able to do this work, since I came here in 2011, we have set up state-of-the-art cryo-EM lab at NTU, including the very latest microscope, Titan Cryos, with all the bits, energy filter, direct electron detectors, faceplate, and so on. And I will explain. It's actually those developments that have led to this resolution revolution. So this is a drawing of the first electron microscope. As we said, J.J. Thomson discovered the electron over 100 years ago. Then they showed that magnetic electric field could focus, act as lenses to focus the electron. And then the electron has a wave. And then in about the 30s, the first electron microscopes were built by Siemens. And actually, the first thought on energy filters, which are quite important, so that you only use the electrons that you want, were developed in the 60s. And finally, in 86, these people here, whose name Benning and Rhodes, received the Nobel Prize for transmission and STEM EM, or scanning EM. So in biology, in order to understand how molecular complexes work, we need to observe these structures. And of course, everybody knows about light microscopy, and the resolution of the light microscope is limited to the wavelength of light, 4 to 700 nanometers. Then more recently, there is super resolution microscopy methods that reach a much better resolution down to 20 nanometer. And electron microscopy, transmission electron microscopy, can now reach, actually, it's now, I should change this, in the last couple of years emerged, you can reach to 2 angstrom resolution for protein structures. So it's starting to really to replace X-ray crystallography. Single particle, 2 to 4, okay? And so this is light microscopy, and I will show you some example of how we capture molecule in ice. Here I think it's a ribosome, and viruses, of course, have been done for a very long time by electron microscopy, the structure of viruses. And it's that indeed where Aaron Klug started by doing the structure of tobacco mosaic virus. So, so the idea of how you obtain 3D structure from 2D images came from Aaron Klug. This is Aaron Klug. And in the 1970s, they published this key paper, Reconstruction of three-dimensional structure from the electron micrograph. And new scientists wrote in the 70s, with the aid of a computer, a Cambridge team has devised a powerful technique for reconstructing three-dimensional objects from two-dimensional photographs taken in electron microscope. The technique promises to revolutionize the study of biological structure. Here, one of them describes the first result applied to spherical viruses. And Aaron got the Nobel Prize in 1982. So there are 2 methods to obtaining three-dimensional structures from 2D images. So because of molecules, because the way we focus a beam, because of the large depth of focus, one single TEM image represents a projection. So it's really this, a projection or a shadow of the object. So in single particle EM, we combine images of different particles, which means we combine, as you will see, really the different views of the same particle to then calculate the three-dimensional structure. In tomography, it's an alternative way. You basically put, and again I have a little movie if I get to it showing this, you have your sample on your grid, but then you tilt the sample, okay? Plus, minus, all we can do is like plus, minus 70 degrees. The beam is here, so you will get different views of the same particle. Here the resolution is somewhat poorer, 8 to 20 angstrom, but it's also getting better all the time. So in the last few years, there's been huge advantages both in single particle EM, and I will also talk about something that's very interesting, a particular interest to us here is correlative light and electron microscopy, combining light microscopy with electron microscopy called CLEM, because this method actually allows you to observe and determine the structure of complexes inside cells. And this is really, I think, we can now say that this field is in a way saturated, but this is the emerging field, that we no longer need to isolate structures or produce them in the test tube to do EM, but we can look directly inside cells. And cryo-EM received last year's Nobel Prize. That went to Richard Henderson, who did actually one of the first structure of a cell receptor bacterial rhodopsin using 2D crystal by using electron microscopy. Jacques Dupuget figured out how to freeze samples so that you form vitreous ice. So in order to do this, we have to put samples and freeze them very quickly. We want to avoid getting ice crystals, and you do this in liquid ethane. And then Joachim Frank really was one of the first people to apply the method and work out the computational method, and he applied it to the ribosome. And so this is a microscope in 1933. Siemens, it looks like an electron microscope. We now have this wonderful microscope from FEI, who was bought up by Thermo Fisher last year. And we already noticed the decline actually in service. I think Thermo Fisher is interested in selling rather than actually building microscopes that work. So, or rather, the microscope work, but the people who assemble them don't seem to know exactly what they're doing. Anyway, now a microscope is just a box, looks like a box, is covered, and it's a 300 kilovolt microscope, has high resolution capabilities. Importantly, we have both robotic sample transfer, which means that we have a cassette in which we can put up 12 or 16 electron microscopy grids and screen them, and we have automated data collection. The vacuum nowadays on this microscope is wonderful. I don't know if people use microscopy here, but one of the pains was that the filament would go all the time because the vacuum wasn't good enough. But now the new scopes very well cooled, and we have very stable, so we can do long data collection. And we can do it remotely. It's all computerized. And also it has dual axis tomography capability. I told you about tomography, that you tilt your grid plus minus 60 or 70. Of course, this has limitations. So basically, in order to overcome that, you turn your grid by 90 degrees, and then you do another tilt series. And we have very large area detectors. So basically, we do high throughput data collection, and I can tell you one of these microscopes produces 2 terabytes of data a day. Okay? So then the next question is, how do you deal with that data? So you have to set up quite sophisticated computation, which we had to do here at NTU to be able to analyze the data. So this resolution revolution, as already alluded at, it really is due to multiple developments. So instrumentation, automation, I already told you about. We now use direct electron detectors. This is big breakthrough. You may remember in the early days we took photographs, and then CCDs came in to collect data. Really bad news because of the pixel size of CCDs. So you would do better collecting data on film. Nowadays we have direct electron detectors, and now we can actually do direct electron counting, which means we can collect data immensely fast. And we actually collect data nowadays in movie mode, meaning that we collect a very fast movie and then can select the best images from that movie. And there are really 2 main manufacturers in this area. It's the Gatan K2 or K3 camera and Falcon 3, actually, who was developed primarily by Richard Henderson in Cambridge. And then we have faceplate, which faceplates, people have talked about these faceplates for 50 years. But I think never got them to work. They were not stable enough. But finally, it seems like stable faceplates. They have the problems, but we get huge, as I will show you, contrast enhancement. You know, with any microscopy, it's really the signal to the signal ratio, to background ratio that's important. And of course, in cryo, we don't use stain, right? In the old-fashioned old time, you would have to use negative stain to see your biological molecules in the microscope. Now we just do it directly in ice. And the computational method for image processing and structure determination have been revolutionized, firstly by use of Bayesian approaches, or maximum likelihood approaches. And what's coming in now is machine learning. So we have to switch from using CPU to GPU setup. It also, of course, means that going from CPU to GPU, we can analyze our data about 50 times faster with one GPU card versus 200 CPUs. And I put this in, most innovation from come from scientists doing basic research in academic institutions. I gave this talk at the MedTech Asia meeting where there were all technologists or companies. And I wanted to make the point that actually the big developments in any field come from academia. And here is a little movie that explains from Jürgen Plisko how, so we have molecules moving around in water. And then they get flash frozen at minus 180 degrees. So now we have captured the molecules in a hole in the EM grid in vitreous ice. Then the electron beam comes, and you get the projection of the molecules, which we call particles, actually. And in this image, you're supposed to see that the particles have different orientations. And then the whole idea is that we call it pick particles. So we pick tens of thousands, millions nowadays particles, which basically is different views of the same molecules, okay? I mean, it's obvious to anybody if you see an object from all possible orientation, right? In your head, you can reconstruct what that object looks like. We do it to computers. So basically, you try to fill the whole three-dimensional space. And then you have the 3D structure of whatever object. I can't even remember what this is. It's some fancy enzyme. Here at NTU, we concentrate a lot on chromatin, and particularly in telomeric chromatin. And I will tell you about our effort to determine the structure of the nucleosome core, which is the building block of chromosome, and then this really important enzyme called the telomerase, which is upregulating 90% of human cancer and adds telomeric DNA repeats to the ends of linear eukaryotic chromosomes. So one development is this new phase construct method for transmission electron microscopy. So the fundamental limiting factor in biological cryo-EM is radiation damage to the sample caused by electron beam. So this limits the dose and leads to low signal-to-noise ratio. And that's actually originally one of the reasons why we freeze sample. It's just like in exocrystallography, when we went from X-rays in the lab to synchrotrons, we had to figure out how to freeze crystals in order to preserve the molecules. And recently, Radoshtin Danev in Baumaster group in Munich developed the Volta faceplate, which is really a thin film plate originally proposed by Zernike. So it comprises a very thin 10 nanometer continuous amorphous carbon film constantly heated at 250 degrees. The phase shift is created on the fly by interaction of the central diffraction beam with the film. So when we collect data, you have a wave, and you don't know you had, before the faceplate, we have no way of knowing where in the amplitude of the wave we were collecting the data. And I just show you an example of this done here at NTU by my colleague Sarah Sandin. So originally, the structure of the building blocks of chromosome was done from crystallography. And actually, I grew the first core crystals in 1976. And it took over 20 years. So I crystallized in 76. We have 7 angstrom in 81. And then it took another 16 years to get to 2.8 angstrom resolution. And in between here was another great technological event. The synchrotron station came along. Okay, this was determined in-house with an X-ray generator. And the nucleosome, I think, is a very beautiful structure where you have a protein core onto which about 150 base pair of DNA is wrapped. And this is a conserved structure right through the animal kingdom. And here is an example of using the faceplate. So this is a nucleosome particle. This is in what you see in the electron microscope in the absence of the faceplate. And here is with the faceplate. So in order to do the structure, we have to be able to see our molecules in the eyes. And this is a difference. And actually, quite amazingly, you can see single DNA molecule by eye with the faceplate. So people already started doing nucleic acid structure just using cryo-EM rather than crystallography. And this is, shows the phase shift, I suppose. And the main thing is that I'm not going through how we collect data in EM, but it allows, the faceplate allows data to be collected in focus rather than out of focus, like we normally have to do here. Okay. And here you see a field view, then we do the 2D classes, different views, and you see even in the 2D classes already, you can see the helical shape of the DNA. And then we reconstitute the structure. Basically means we can basically get atomic structure resolution. And I told you it took 20 years or so, 76 to 97, 21 years to do it by crystallography. This was done in 3 months, only using 22,000 particles, okay? But also this number tells you something else. It means that you can determine structure with extremely little material, and most of the complexes biologists are interested in are not abundant, and they're very difficult to reproduce in the test tube. So instead of, when I used to do nucleosome core prep, I had to produce 50 to 100 milligram of nucleosome cores in order to crystallize them. Now you can do structures with very little material. In fact, people now tagging protein, the part of complex inside cell and pulling out the whole complex, like the spliceosome, and they can do the structure at near atomic resolution. How am I doing for time? So I already said the telomeres or the tips of eukaryotic chromosomes, and did I take, yeah. So I'm going to tell you about now the telomerase structure that we originally did by negative stain whilst I was in Cambridge, and now we are doing it by cryo. And so telomere biology, telomeres are a very important structure in biology and medicine. They protect chromosomes from degradation and infusion. Uncapping leads to genome instability. So they are DNA damage hotspots. Short involving cellular senescence. Normal cell aging, so we lose about 100 base pair of telomeric DNA a year as we age. Quite a scary thought, but it's a fact. And then, of course, there are premature aging syndrome, which provide quite actually nice model system to understand the aging. And then this enzyme I'm going to tell you about called telomerase is actually upregulated 90% of human cancer. That's why cancer cell lines are immortal. And as has been shown experimentally, you can immortalize cells simply by expressing telomerase. And I'm not going through, but basically, already Jim Watson proposed there had to be a reverse transcriptase to add DNA. Otherwise, every time a chromosome or DNA is replicated, because you have an RNA primer, you would lose DNA from the end of chromosome. And he proposed there should be such an enzyme. And they did, such an enzyme was found. It's it's a reverse transcriptase, which encodes its own template, has an RNA molecule that encodes the template for telomeric DNA, which I don't know if I made clear, it's incredibly repeated. So in humans, we have TT, this is a different organism, but in human, we have TTA, GGG, repeated for 10, so we have 10,000 base pairs of DNA with this repeat. And the third subunit was identified by Blackburn and Grider in '84, for which they got the Nobel Prize a few years ago. And then the protein subunit, there was quite a race to try and find it. It took 13 years to find it, and it was found. And so at that point, we started working on telomerase, and we knew what it consisting of. And it's been a very, very difficult problem, because even in cancer cell, you only have 50 copies of this enzyme. So we had to produce it by overexpression in mammalian cell and purifying it. And this has been a huge bottleneck. And it's taken years. But anyway, we are sort of there now. So this is, I can't spell particles, obviously. Telomerase particle capture in ice. And here is what telomerase looks like in ice. Okay, and this is on our new Titan cryos at 300 kilovolts, and we used graphene oxide. I think someone measured graphene backgrounds yesterday. So we use graphene, we lay graphene oxide, or graphene actually, over the EM grid to help to capture the molecules. So you can either capture them just in ice, in holes in the grids, or lay graphene oxide. Normally, people used to use carbon, but graphene is much thinner and much more stable. And this is the EM processing. And this is just an example how what we can do now. So basically, we collected many micrographs, 5,000 micrographs. Out of this, automatically pick 770,000 particles, and then classified them. We can throw out all the bad particles, classify in 2D classes. So these are side views, top views, and then the good particles go into 3D reconstruction using an initial model obtained by tomography. And so we can start classifying the telomerase into different complexes. So we have resolution about 10 angstrom right now of the particle. And the molecule is very flexible, and so one way we get over it is we mask one half, and then we get better resolution of the other half, okay? I think I'm running out of time. So the need to study biological system, I'll go through this very quickly, on different scales from atoms to cell, will make, so correlative method will be indispensable. I think this is dying. Dispensable, correlative method dispensable, and it will worth investing resources. So we are now going toward hybrid technologies. This is the method that allows you to look inside cells. In order to do that, we use this genetically encoded tags that are both fluorescent. They are fluorescent. So we can go inside a cell and say, OK, my molecule of interest is here. And I will show you. And this, but in this particular method, the tag is Minisog. It was invented by Roger Chen of GFP fame. And then through a chemical reaction, we can deposit osmium. And this is what you see. So this is our transfected cell. And you can see the fluorescence dot that represent telomeres. And then through this chemical reaction, we see deposit osmium. We see now electron-dense dots, which we can focus into. And we use, in this instance, we use tomography, okay, instead of single particle. So we do tomography. And actually, the latest development is this cryofib developed. So I'm not going to go into this, but we have bought it. It's called the Aquilus. It will arrive soon. It's basically you freeze cells on electron beam, and then you use, or on electron grid, and then you use a focused ion beam to create a very thin lamella. And then you image that lamella, and the reason you can image it is because we can now use the faceplate. That gives you much higher contrast. So there will be no need for any staining, and you will see molecule inside cells, so complexes inside cells, without any fixation or staining. Okay? Here tomography. I'm running out of time. So tomography, I already alluded how it works. Notice that the sample is tilting. So here the sample holder, it tilts in one direction and the other. And then when we back project the images, we can reconstruct the three-dimensional structure. Okay. And here is a reconstruction done by Sarah Sandin. This is what you saw before, a telomere inside a cell, right? Using tomography. This is a 3D reconstruction of a telomere in situ. And the resolution, I forgot to say, is about 10 nanometer. So, you know, about 10 to 100 times better than super resolution microscopy. Shall I stop there? And I want to thank Jürgen Plitzko, who provided me with the movies I showed you from Martin Street. Sarah Sandin, she did the nucleosome core work. She was my postdoc in Cambridge. She's now a professor here. And she did the work on the nucleosome core and the telomere, and my group for the work on telomerase. Thank you.
So I actually have two questions. First is when you were talking about the, I guess the telomere work that you did,
yeah.
You said you pick the good particles. Or
yeah.
good. How do you know what's a good and what's a bad?
Yeah, you go back. So there are two ways. So you know, the best way is actually pick particle with your eyes, okay? You select particles by just looking at them. Yeah, but you know, to collect, nowadays you very often see structure where people have collected huge data with 1 million or 2 million particles. The only way to do that is to use automatic data picking. So basically you have to go back, you collect your particles, you do 2D classification, and then you go into each 2D class and you throw out what's bad.
But how do you know what's bad? That's what I'm not.
No, so probably the soundest way of doing it is to calculate the low resolution three-dimensional structure, and then in that way you have a three-dimensional mask, and then you apply that mask to all the views. So it's really a cleaning up method.
So something that just doesn't fit in the mask at all, you know is.
Yes. Because although we now can see this molecule, and I didn't make actually another point. People thought in electron microscopy that you could never image things that were smaller than 500 kilodaltons, okay? Because you have to be able to see your molecules. It turns out it's not true. The size, people now done the structure of hemoglobin at atomic resolution. But there is still, although we can see our structure, the background is still quite high. It's not perfect. So we still struggle with, you know, telling, particularly a computer program, telling what's a real molecule and what's noise in the background.
And we might run out of time,
yeah.
But the other question is, in sort of a very simple way, can you explain how these phase plates work? How they make world better?
I can't. And I think actually even the people who have built them don't understand really how they work. I only know that they work. But basically, if I've understood correctly, you have a wave, right, of the electron. And when you image your data, you don't know where you are on that wave. So by shifting the phase, you get, I suppose you collect more data at the top of the wave.
Probably
but
understanding
yeah.
Equivalent to
That I understand. I think many people understand that. No, but it is true. It's not quite understood. And it's really a novel thing, and we're still struggling with actually getting them to work properly, because what we have is it's a very thin carbon film, and they test it at the factory. But when we put it in our microscope, it's fairly clear that the film has sometimes ridges on it. So your molecule, you think you image your molecule, but they're actually at different level in that film, and so on. But I think they will figure out how to do this better. And of course, the face plate only lasts for a short time of collection. So then you have to move to another area to collect.
I was Ahmed graduate student, since 1993. Joined the Ahmed group, and then finished PhD there. And then he asked me to stay for postdoc. At that time, actually, originally he asked me to do electrons, because as Jim mentioned, that is a critical time in 1999. Ahmed Group working for 10 years for electrons. That time for electron diffraction. I guess that time is the critical stage for a major advance in the electron diffraction in end of the 1990s. So I joined his group at the beginning, wanted to do electron diffraction following Mach standards. And that time he told me, no, there are too many people in that room, you do optical. So that's why I did my PhD in optical studies. And then for postdoc work, and actually he asked, no, now you can back to electron diffraction, And then, that time, lots of the difficulties in that area. So, in order to escape quickly, from global, I said, I'm not doing electron diffraction. I want to do another direction, which he originally really wanted to do biology. I say, I can try that area, started to maybe learn biology. So that's why I decided to stay in his lab to do so-called femtobiology, this stuff. I mean, through the many years, I stayed 3 years. I left 2002. So total, I spent roughly close to 9 years at Caltech. That's why I know most of the people here, and then in Zewail group. So through the years, I have to say I learned all the science from Ahmed. Really, early days from China to US. Really, we don't know how to do science in general speaking. So basically, I learned everything from him. How to see the problem, how to understanding, how to thinking, all the details. So here I show a few snapshots. After I left Caltech, we always keep a contact. Basically we see each other, once a year or twice a year in different occasions. Sometimes also I back to Caltech to visit him. I guess this picture took, 2003 or 2004 in the summer. And then this picture took in Oxford when we have Femto conference by David Clark. I guess it's 2007. And then this is in 2004, and this is the second time Ahmed visited China with Dima, and then I went there with them in the whole trip. And this is, I'm sure many Chinese students here and quickly recognize this is the Yu Garden in Shanghai. So we had several days in Shanghai. So during the trip, we always discuss science, in general, and also many problems in society. So that's I learned lots of the things from him, both from science and also as the human being for many things. So and then unfortunately he passed away. So I'm luckily and then also with Majay, he's really played a leading role to edit the first book, and then we have many scientific family member requests And then we started working in the do-how, and then we quickly put the second book in press. So many people will see books, out of in the hallway, And then, luckily, if you are interested, you can see lots of the interesting stories, and also the major science discovery through the Ahmed's lab. And then we collect the story from the early days when he joined the Caltech, and then all the way to the 2016. I think it's a very, very, very lovely book, and then definitely it's very inspiring. So, and also we have several meetings for him, and then I guess this probably is the first meeting especially devoted to Ahmed Zewail memory, And then we did have several SS meetings last year for Ahmed Zewail award. And then in summer in Boston, we have 5 days special session for him in SS meeting. I'm sure many people will be there again. And then next year we have a meeting, Femtochemistry 14. As decided in Cancun, we'll go to China. And then I guess that was 20 years Nobel Prize in chemistry by Ahmed. And then I said we will have some maybe celebration there also next year in the summer. We will decide the time very soon, and then everyone will receive the notice for this week. So it's really great, to have all of you here, and then to celebrate Ahmed's legacy. So right now, let's back to science. And then since I temporarily decided to take this slot, and then I try to quickly show some very recent work, even we do many years already, but we haven't published anything about this project yet. So hopefully I can show you some complete story for this system. I'm sure many people know my group work probably about the photolysis, which is the DNA repair enzyme. We started for many years, and then try to solve all the details. So this is probably the second system we try very hard, and then try to solve the complete story for this biological machine. So quickly, I will give very brief introduction. Then for this photo machine, basically we separated 2 major parts for this machine function. And one is the energy transfer, which is a very surprise to us after we see the structure. And then secondly is the key mechanism of how these machines work. So all the data presented here is not published here. It's a fresh data. So quickly, I'm sure many people know in the audience, and then UV is not good for human being. And then first thing, for example, DNA damage, which we started also for a while, and then also recently gave the Nobel Prize to 15 to 3 gentlemen. And one of them is our collaborator, Aziz Zenya, and he studied this DNA damage for his career. So the UV will cause this DNA damage, and the 2 major forms is the so-called CPD and cyclobutene pyrimidine dimer. And then this is in the same DNA strain, it's easily damaged, as Daniela also mentioned in the telomerase and chromatin, and there that end the DNA easy to be damaged. And then also another major, this is 80%, another 20% in the cell, and the DNA damage by UV light is to form this very strange structure called the 6,4 photo product. I guess even named the chemical nomenclature is very long name. So people give the simple name. This is 6 position, 4 position. So this is called the 6,4 photo product. That means by UV damage. Of course, if you look at this structure detail, and then this is a base T and T, and just cross this 2 bond. But if you look at this structure, it's very complicated. you migrate the hydrogen and the oxygen to the another base. So this is a very complicated chemical reaction to get this strange form. And then we did some studies by photolysis enzyme, both repair this and this. But UV is really not good for DNA. And also UV can cause this oxidative stress, produce the O2 minus and OH radical, and this is very harmful to the biology of for molecules. And then of course I'm sure many people know if you're doing biology, and then also UV we are impairing photosynthesis and then by damaging all this stuff. So, and the scientists for a long time, especially in plant biology field, people thought there must be some UV protection system. But for humans, you can go to the inside in the shield and you can avoid the UV exposed. But for the plants in the nature, you couldn't do that. So the plant scientists for a long time to think about it, there must be some UV protector system. In order to that, you have to have a UV photoreceptor to trigger the whole system. So finally, in 2011, and then scientists pinned down this UVR8 is, there's some UVRA, UVRB, all these names. And the UVR8 one protein is determined by German scientists. And then this is the UV photoreceptor existing in nature, and then to pin down. And then immediately next year, there are two groups. One is in China, and Yigonshi, right now also the major force doing the by EM. And then also the get-off in the script, and published two papers in the same month, and then one Nature, one Science, to solve this photoreceptor structure. If you work in the photoreceptor field, this is, you must get a structure, and then you understand how this, photo reaction pathways. So then we are, when we saw this structure, we are getting very excited because this photoreceptor has no chromophore. No, now, if you look at a red photoreceptor have the beating chromophore, and then if you look at a blue photoreceptor, you have the flaring. But for this one, no chromophore, and only, not only, this protein has a lot of the tryptophan, which is intrinsic amino acid, and it's active as the chromophore, as this protein. So I thought this is extremely exciting because we started tryptophan for my career. So we say we definitely has an advantage to study this system. So, and then after this, many people studied this biology function for this UVR8, and then I just list a few. And this photoreceptor, like many other photoreceptor, exist in nature in dimer fashion, and then always in dimer. And then with the light, if this is a visible photoreceptor, where visible light, this is UV, and then extremely this is sensitive to UVB, and the UVB is roughly around 300 nanometer. And with the UVB radiation, this dimer first step will become the monomerization, become monomer. And then in the cell, this monomer can quickly bond with called copper-1. Copper-1 is a critical protein in plant biology, played many roles in the in plant biology. So this UVR8 monomer will bonding with copper-1, then trigger a serious biological function in the nature. And then, for example, they can help DNA repair, and then also circadian rhythm, and also photomorphology things, and even flowering, all these things. So, which is very important, event or biological function in the nature, So then let's back to this molecular structure, and then what's going on with UV absorption and how they dissociate to the monomer. So for the first step. And if you look at this structure, and then you can see this is a dimer. And then for each monomer, there are 14 tryptophans. the chromophore. And then besides the one tryptophan on the 1C terminal, which is low structure, it's a Hoy type. That's the 13 structured tryptophan formed in this fashion. One, this protein is like propel, so have 7 braids. Each braid has 3 beta sheets. So all beta sheets protein. So it's like cylinder, and the middle is the hole, the middle hole, and then 7 braid, and then and each braid 3 beta sheets. And then if we look at this protein, and then there are 6 tryptophan here, form the ring in the middle of this protein, and one is by tyrosine, by evolution or something reason. So that's a 6, and tryptophan form this ring in the middle. And on the interface, according to axis structure, there are 32 iron salt bridge, and the hydrogen bonding. So this protein looks like a rock. It's very hard to dissociate, just by this strong interaction, So at the interface, by close to the C2 symmetry, they form. Look at this interface. There are 3 tryptophan in the center here, and form the cluster, and with a lot of tryptophan coming in, form so-called pyramid. They're like a pyramid shape. And then around this pyramid shape, and then there are another 3 tryptophan formed this like a half small ring. We call the peripheral. So this is 3 peripheral tryptophan, this is 3-1, and then form here structure. So that's another pair, vice versa. So at the interface, there are 14 tryptophans at the interface. So, and then by lots of mutations, and then biological scientists already figure out this one is extremely critical for initial photochemistry to start the signal. So, which I'll back to later. So even you look at this structure, we are that time immediately thinking, looks like a photosynthetic system. This tryptophan must have some biological function. It's not just only for structure. Of course, the structure also important. It has to biological function. So that's what we started with, and then we immediately contact Yi Gong in the Tsinghua in China, and he sent a plasmid immediately. So we started working on this from 2012. So we did hundreds of mutations for this protein. Basically, everything you can think of, we all did. But here I only showed some key stuff here. So first we mutated this so-called very important 285. There are 2 tryptophan in this at the interface, extremely critical. One is 285, one is 233. Without either one, this dimer will not dissociate. Like a dimer is rigid no matter what you do. So you mutated either one, you couldn't do that. But then you have to this 2 tryptophan, 233, 285, coexisting there to do the biological function to dissociate. So we quickly mutated 1 to 85. We find out that the quantum year will jump to, this is a Y-type emission. This is typical tryptophan emission. And then without this 285, this emission jump to here. It's huge. And then the quantum year is 0.42. The Y-type, the quantum year is 0.07. By simple estimation, you immediately know there are some energy transfer between tryptophans by this single estimation. Has to be. So then we say, well, that's good news. All the tryptophan who have the energy transfer between tryptophan and the tryptophan. So now this is a very busy slide, also very important. Here in this talk, for the first part, let's look at the first 3 mutants. So just follow me. For this notion, when we write 6WD and plus 3WP means we lock out all this center pyramid tryptophan. So basically, we keep this 6DWD plus 3p, we can lock out all these 4 pyrimidine tryptophan out. So, and then when we write 6WD plus 4WC, basically we can lock out these 3 peripheral tryptophan. We leave this pyrimid at the interface, and then keep this 6D. And then, as long as you, without 285 and then 233, this molecule always die, no matter what they're doing, always die. And then next thing is we spend more than half a year or 1 year to finally to get this monomer, because in order to understand this, we have to have the emission peak and the lifetime of this 6WD tryptophan, optical property. And then you couldn't get it. And then, of course, you can ask, say, you just keep a shining light and then become dissociation monomer, you can get a monomer. However, after dissociated, the monomer structure is different. So we want to this intact the monomer tryptophan information. So that's why we screen many mutants. Finally, we get one. We mutate all this interface tryptophan, which is 7 in each monomer, and then we need to mutate one critical amino acid, and then we become beautiful monomer. So in this way, we can do each these 3 groups. We make the absorption, emission, and by simple deconvolution, we can precise get the 6 distal absorption WD, and the pure peripheral this absorption, and the pure pyrimid, this tryptophan in the center is the absorption, and also we can pump get an emission peak. So we have 3 different group tryptophan in this structure, the absorption and the emission. That's good news, because if you look at this overlap, you will immediately say they are energy transfer, even by simple forced transfer mechanism. And then also you can see this WD will transfer energy to peripheral tryptophan, this 3, and also transfer energy to this center. And the vice versa is very small. So the energy transfer in one direction. So basically the 6D energy absorption transfer all the energy to the interface, And then similarly, also you have the peripheral tryptophan transfer energy, absorb the energy to transfer to the center. So in a word, that means all the energy absorbed by tryptophan from the beginning transfer this circle tryptophan transfer to the interface, and at the interface the six peripheral transfer energy to the center. So all the energy UVB finally funnel the energy to the center of the pyramid. So with this order in mind, and then we say we can figure out how this dynamics of the energy transfer. So we can quickly use a Fredholm formula to estimate the use X-ray structure. You can construct all the tryptophan pair, because this is a dimer. So if you look at finally, they have 168 tryptophan energy transfer pair for this WD to the interface, because this dimer, so there's another side, this lines. And at the interface, this peripheral, and each tryptophan will transfer energy to this pyramid center. So there are another 24 at the interface transfer. So add together close to 180 or 190 tryptophan energy transfer pair. Okay. So then we go to figure out all these details in the lab by the mutation. So then we quickly do one thing I need to emphasize a little bit, and then this is very critical. Otherwise, we couldn't do any experiment. This is very important. If we look at the pyramid tryptophan, the absorption tail go to the 320. So you can think about, if we tune the laser here, the very end of the tail, we can precise only pump the pyramid tryptophan only. And then with mutation this out, and then the peripheral, the absorption tail go to 315 here. And then we can tune 310, and then we know we precise pump the peripheral tryptophan. So by doing this, we can precise pump each group of tryptophan in this structure. Then we can tear apart all the dynamics. So that's exactly what we did. So first thing, we did this 3D with 1P. We can mutate out all the pyramid tryptophan in the center, and also we only leave one peripheral tryptophan. We can do, then we have 1, 2, 3. There we have 3 mutant. We can make the time resolved spectrum. And then we also can put the 2P. We have leave the 2 peripheral and mutate all this pyramid, the pyramid tryptophan and another one. So we also can do all 3, and all we can put the 4WC without the 3WP, and then we can do all total together. So we can do all the combination time resolved, and then we can go to the fit this data, and then this is the summary of the result. First thing, we need to figure out, as I said, we need to know exactly this monomer, the 6WD, the lifetime. And by precise determining this tryptophan lifetime is 500 picosecond is 30%, and the 2.7 picosecond 71. The 6 tryptophan on the ring is symmetry. So we just treat this 6 tryptophan as the 1 tryptophan. And then we load the lifetime. And with this mutation, now we add 1 by 1 on at the interface. So then, as I showed you previous, the time resolved data, then we can decompose this component. And then take this figure to see. This is this mutant, the total emission peak. We can decompose. There are 2 components from the 6WD, and you can see here. One is 500 picosecond, another is 2.4 nanosecond. Why is 2.4? Original 2.7 because it's energy transfer, as I showed here. With the energy transfer, this lifetime becomes 2.4. That means this one is also nanosecond. So energy transfer is a nanosecond. Also distance very long is 20 angstrom. And then another component, of course, you also pump the WP. So this 8 nanosecond roughly is the WP emission. And the single point is the deconvolution time resolved data. And then the solid line is direct measure the mutant, the emission peak. You can see this is matched very well. That means the way you deconvolute all the data, it is valid. It's matched very well. So by doing this, we can do all kinds of the mutation to deconvolute to figure out what's the dynamics inside. And then also by doing this, we can simulate, use flat the data, flat the calculation data. We can simulate the energy transfer and put it together exact the same as the number we get from the experiment. So by doing this, we saw that this flat is perfect. For this long distance energy transfer, the flat is working. The flat mechanism working perfectly fine. So that's why we finish the WD to transfer energy to the interface. And then next is we need to figure out how the WP to transfer energy to the how much time? 5 minutes. And the WP how to transfer energy to this center. So then we need to do the each mutation, and here we only pump 315. In this way, we pump only WP and the pyramid, and then this. And then first we prove among this 3WP that's low energy transfer, and they only transfer to the center of the pyramid. And then we can cap, for example, here we pump 315 with the Y type. You can see we find that here is about 70% is quenching, which is 80 picosecond, and 1.5 is 30% is 1.4, 1.5 nanosecond. And then by doing all this mutation, we also find out in the pyramid center, that's only 285. 285, 233 is important. If you mutate other thing, other W94, also W337 in this pyramid one, its dynamics no change. That means in this pyramid, even you remove another 2 tryptophan, it's still function, and then will not affect. But then, if otherwise, you will get a different thing. And then also we do all this time resolve, same as before. We can go to deconvolute. All the data we can deconvolute, all the mutation. I just quickly give this final result. We can measure each WP, the data, the lifetime, and then we also can measure each 2 WP, the dynamics. Similarly, we can decompose the time resolved spectrum. One is direct measure each Newton, and then all we can do time resolved decompose with the dynamics built in, and then we can match this perfectly. So in this way, we can figure out all the catalytics, the energy transfer from this 3WP to the center. So finally, I quickly summarize here, and then with the UVB, they absorb here 35% direct in the center, and then they absorb the 48 is in this in the ring and also peripheral. And after this initial absorption, there are 34% transfer from the ring to the center, and then 10% to the peripheral, and the peripheral absorption transfer 75. So these are all the energy funnel in these molecules. Since the time I quickly, this is summarized, basically I already told. I quickly mention just next one. And then, by the way, this energy transfer, all the detail, and also very happily, I came here every year. So also we had a very detailed discussion with Mabi, and Mabi with Ludi in the 2014 also predict that this energy transfer has to happen in these molecules. Yeah. So quickly in 1 or 2 minutes, and then the key part. Okay, actually this is the most key part. After energy tunnel to this center, what's happening? And this is take a few years to figure out. And finally, energy in this pyramid has a charge separation with the WW, which we are surprised because in literature we go to find out nobody report the WW will do charge separation. So we finally figure out that this in cluster the charge separation is 80 picosecond with the WW. However, there are 4 picoseconds where to charge recombination. So actually it's very difficult to charge separation. And after charge separation, they are bound again. So however, there another channel is 17 picosecond. This selective will neutralize this arginine, the positive, one salt bridge. So when they neutralize the salt bridge, now something happens like a domino effect. Then they start to zip the interface, the whole salt bridge. And how? And then we collaborate with Johnny Gao in Minnesota and did a long time calculation. Right now we already run probably 10 microseconds, more than 10 microseconds. And then it's very surprised to us. At the beginning we also thought about this, but finally MD also proved. So after this negative neutralized with arginine, and the salt bridge, first salt bridge broken. And then I told you in the middle there's a water hole. And then when this charge separation, the tryptophan move, and move this water from the hole flooding into the interface. And after first salt bridge neutralized, and then the water squeeze into the interface. So end of day, it's by water and solving the charge, then zip the interface. So I told students, in order to destroy the building or house, what do? Of course, you can fire, which is not good. And very simple, just fill all water in, flooding this in the house. The house will destroy. So this exact happen here. After this initial, the neutral separation, charge separation, and the neutral neutralize the one salt bridge, and the water start to play the role, all the move in. and then zip the whole interface. It's a very rigid interface, very rigid interface. So anyway, finally, this is the OSU team, and then most of the work done by Xianpeng Li, and then also graduate student Maniak, and then Zhiying Liu, and also we have a protein scientist to make all this mutation work. And then MD simulation and also QM calculation done by the collaboration through the collaboration by Johnny Gao. And then initially we get a help from the Yibong Shi from Tsinghua, and then the funding supported by NIH.
Very nice talk, Dongping. Congratulations. This is really beautiful work. I had a question. You tended to attribute the relatively slow energy transfer to the distance. But I have the impression that what is playing a bigger role here is poor spectral overlap, more than the distance. Distances are typical of biological systems, but I think the spectral overlap is a key factor.
Yes.
For the second time.
So good morning, everyone. So first, I would like to really thank our earlier speaker and organizer, Professor Dongping Zhong, for the opportunity to be here. To join a wonderful group of people celebrating one of the greatest scientists I know of, right? Of his lifelong scientific achievement. One thing that I wanted to point out is that, of course, Dongping mentioned briefly. So we have heard from many speakers the contribution in many areas from Professor Zewail. But one of the areas which touched my heart, where he also made tremendous contribution, is biophysics, and in particular is protein folding. So at least in the last 10 or 15 years of his scientific career, so he spent a lot of time the tools and the method trying to understand one of the very important yet very complex problem, that is how proteins fold. We have heard this morning talks how important those organizations can come together to really maintain life, to deliver functions of all kinds. So in this regard, so I will share with you a few stories coming from my lab with regard to really understanding the underlying sort of features of the folding energy landscape of protein folding. So I'm compelled to, of course, to link myself to the Zewail family. So some people in the audience know me. Of course, I'm not really a direct member of the scientific family of Professor Zewail. However, I'm really intimately related to him through actually another great scientist. Of course, many of us, I guess, who are familiar with ultrafast laser spectroscopy know this gentleman. One of my former colleagues who unfortunately passed away a few years ago, Professor Robin Hofstresser. So of course, Dr. Zewail did his PhD with Robin Hofstresser. So the connection, of course, is twofold. One, of course, now I'm teaching at that great department. Of course, having said that, I don't mean that I'm a mentor of a great scientist, of course, but I mean, just by chance. So there's that connection. Another connection actually is that my postdoc advisor, Philippe Anfrud, is a postdoc of Robin Hofstresser. So through that connection, I guess I can claim that I'm a cousin of you guys, academically. Anyway, so now let's come back to science. So, so theorists have come up with this great idea describing the underlying driving force and the mechanism of protein folding. So basically, the idea is that the evolution has made the inner landscape of protein folding biased toward the native state. Of course, in order to understand the dynamics, the picture would be that you have an ensemble of unfolded proteins, which coming down or diffusing along a multidimensional energy surface due to this energetic bias, they would, after some time, coming down to one of the wells, which we call a native state or a state that can deliver function. So this is one picture, but for those who are doing experiment for a living, it is pretty difficult to relate it to. The reason is that no matter what you do, using, of course, the language of Cassie, so you have a reaction coordinate. So the question is that I'm pretty sure Stu will also use this type of picture. What is our reaction coordinate? So we don't have a choice. The reason is that the reaction coordinate basically is the signal that you probe. Okay. So of course, Dongping has give us a wonderful story utilizing tryptophan fluorescence as a probe of function and dynamics of proteins. Of course, when you study protein folding, you could also use that as a proxy, right, to follow the conformational change from unfolded to folded state. So in that regard, depending on the choice of your coordinate, you may come up sort of simple-minded pictures that, of course, is really a projection of a multidimensional problem onto a simple two-dimensional plane. That may, of course, for the simplest case, you have just a barrier, as we are seeing from Cass's peak talk, right? So that means that the unfolded state is connected through this barrier to the folded state, and so on and so forth. So of course, just because the enormous complexity or the large number of conformation states involved in the folding process, so you may encounter, of course, other more complicated scenario, which means that you may have intermediate state and so on and so forth. And at extreme cases, maybe that the folding process does not encounter any barrier. So which means that you really have a downhill process if the bias toward the native state is very high, for example. Well, this is all good, right? This is what we want to teach at the undergraduate level. But even that, the question is that how would you relate for a particular system, the structure evolution to those energetic terms, which should be free energy, of course. We do experiment, of course, as I said, that we could use a wide variety of different signals. Of course, again, the problem is that it's very difficult to relate to what you probe to this type, simple side of the picture. So not only that, if you think of the problem a little bit harder, you would realize that, of course, the free energy surface is not necessarily very flat or smooth. Actually, just because you have many side chains or gazillion tryptophans, okay, we just saw one, right? So things want to come together in the folded state. So they're going to bump into each other. In other words, is that those sort of native and non-native interactions and quality effect would introduce noise, right, onto the potential. Then the question is, can we design a method which would allow us to look into this roughness of the folding energy landscape? Okay, so this is just, of course, intrinsic chemical physics problems. So if you wanted just to look at or monitor the time scale going from one well to another well, so there are many methods that you could use to do that. But teasing out the fine features of the underlying free energy surface, it is rather difficult, at least that's my understanding. Of course, the goal would be that one day, right, we heard nice talk, the application of electron microscopy, of course, so also family, many of you are expert or trying to design methods that would allow us one day to create molecular movies, right? Which means that we start from a good starting point, then we have the necessary time and also structure resolution, right? Allowing us to construct, right, all the details of the chemical reaction. But we're not there yet, okay? So we have to rely on spectroscopy. So what do we do? Of course, when we do clinical study, we have heard a number of talks already. So you need to have a very well-defined zero time, right? For us, the way of we defining that zero time is to very quickly to change the temperature. We call it temperature jump, right? So the idea is very simple. So you have a bottle of water, and which, if you look at the spectrum, so actually there's a couple of bands, very broad, right, between 1 and 2 micron. So if you dump a lot of photons there, upon absorption of those energy, and the temperature will be rising very quickly. And due to the work of Robin Hostresser and many others, the vibrational cooling occurs on picosecond time scale. So in principle, you could just make the temperature change very quickly on picosecond time scale. So when I started my job in 1999, of course, as well that year we heard won Nobel Prize. So in my department, we had a tradition that is all the junior faculties would do all the dirty work, which means, well, it could be a good one. So you're recruiting and you're inviting speakers. I guess it's good for me. So the first thing I thought, well, let's invite one of our distinguished alumni, right? Professor Zewail. So a couple of years later, well, of course, he was very busy then. So I said, okay, so I finally have time. I want to, come home to visit you guys, okay? So of course, in my office, he asked me that, what do you want to do? I said, I want to do temperature jump, okay, with nanosecond time resolution. So I'm very proud at that time, right? Because nanosecond is pretty fast, right? In terms of time scale you would need to study biological questions. No, he said, no, forget about it. So we can do 3-order magnitude better, right? So we can do picosecond, of course. So that's what they have done a few years back, right? So this is abstract from one of his papers. So for those who can not see here, but I just try to read it, right? We report the development of ultra-fast T-jump with time resolution reaching the fundamental time scale of water thermalization time, 5 picoseconds. The time hits the bulk water up to 20 degrees. Then said the example given here shows the application of the method for the first time, and the results demonstrate distinct time scales for solvation, conformational change, and thermal reaction. So this is a wonderful technique, which in principle is very simple, but nonetheless, due to the intrinsic very fast time scale, then you can sort of initiate, of course, in a general sense, many different types of biological reactions. So this is a major technological breakthrough. Okay, coming back to the probe. So you start the reaction very quickly, but again, what I forgot to mention is that the effect of the change of temperature basically is to change the equilibrium constant. The system, of course, would relax, right, from old equilibrium constant to a new equilibrium position. So what you measure basically is relaxation time, just like what you would do with an NMR spectroscopy, okay, that time, that kinetics. So as I said, that in order to follow the conformation of change, you needed to have a probe. So in our lab, we utilize many ways of vibrational spectroscopy, okay? One of the markers that people in the field use extensively is the so-called the M1 transition. Basically, in a simple-minded argument, is the carbonyl stretching vibration in the backbone of the protein or peptides. Of course, the transition itself involves, of course, is not localized modes, involves contribution from other vibrations. But in a nutshell, it is the single stretching vibration. So why this transition is sensitive to conformation? The reasons are the following, right? So you have a polypeptide when it's unfolded, of course. So due to the random orientations and the separation distance between and among all these transition dipole moments, so you result, the result is that you have pretty broad featureless transition. Upon forming, for example, into alpha helix structure, so you put those transition dipole moments in a much well-defined patterns that the exon coupling would make the band narrow, shift, and split, for example. So that's the reason that it is sensitive to conformation. Of course, in the language of Professor Dongping Zhong, so the interaction between the vibrator and the surrounding water also play a very important role in shaping up the final vibrational feature of the transition. So this is all good, but of course, as I said, that if you really wanted to see anything about the mechanism at a detailed structure level, so this is not good enough. The reason is that you can obviously obtain a signal, but the question is that how would you interpret your signal, just because this is possibly come from all the amateur units that are contributing to the signal. So we don't have a magic, so nobody does. So the practice that everybody uses in the field is to introduce a trick. That is, by changing, for example, the reduced mass of particular amino units. Then, due to the Ostop effect, you could shape the vibrational transition of that amino 1 in particular from the parent peak to a different position. Then when you do experiment, you can look at specific contribution from that vibration alone. So another strategy that we have been playing with is to utilize the so-called unnatural amino acid, especially those who have a small group that offer a distinct vibrational signature. So that signature could be sensitive to a lot of different things, for example, hydration, local electrostatic field, and conformation. Then the idea is that to break down, to take a bottom-up approach, and you collect as much information as possible from one experiment. Then you try to put them together, sometimes in collaboration with people who do molecular dynamics simulations to generate a story. So anyway, so here, just a quick example. So this is a model peptide, very small protein, as it consists of 20 amino acids. And nonetheless, it can form a hydrophobic core, a distinct fold, which is stable. So as you can see that you have alpha helix, you have 310 helix, then you have a polyprotein 2 loop here. So everybody likes tryptophan, I guess. So at the core, there's ring, so which is a very important role to help stabilize this fold. So what we did, of course, to utilize all the information we can gather, so we can selectively put Ostop labels onto this helix or other part of the protein. So here's an example. So this is a different FTIR spectra showing that now you can look at the salt bridge, Dongping mentioned, and selectively detection of the alpha helix, of the labeled region and non-labeled region, and a disorder. Then, of course, you do T-jump, then you monitor and each and every one of the signatures, and at the end, then you can, of course, through the kinetics, so our signal to noise ratio is much worse than what a Dongping has shown. So this is because this is a transmittance measurement, which is much more difficult. So nonetheless, you could put all the information together to generate a mechanism describing the folding pathways of this little protein. What happened is that upon increased temperature, which of course pushed equilibrium to a position where the unfolded state start to dominate. Okay, so what happened is that actually what happened due to the increase of temperature is that you unfold a small 3 helix turn structure in the peptide. Then upon cross a berry, where you sort of destroy the hydrophobic core, nonetheless, the helix is still maintained at the transition state. Then at the downhill side of the folding process or unfolding process, that helix becomes melted. So another example we are very fond of is this different protein secondary structure element that is obviously beta hairpin. So like alpha helix proteins contains either alpha, beta, or both, or mixture, right? So this has been becoming a system for people like myself who are interested in understanding the dynamics of protein folding. So due to the constraint of time, I would not tell you the whole story, but nonetheless, due to our own work and other people's work, and also works from many simulation groups, the folding mechanism of beta hairpin is that they consolidate this beta term first, okay? So at the transition state, which means that you have this very critical hydrogen bond, right? So which lock down this term. So that would be the conformation populated at the transition state. So as a physical chemist, so we very much wanted to get as much information as possible from the transition state, okay? So of course, Professor Zewail won Nobel Prize just because his unique contribution. to look at the structure, dynamics, and energetics of a transition state. Okay? So that's the holy grail. So for protein folding, we have this simple idea, at least for this simple beta hairpin system, is that would it be possible actually to engineer an analog that would position itself, right, at the transition state, right? So for those who are familiar with studies of enzymatic reactions, right, people in that field always create analogs that mimic the transition state, right? In other words, that they have a very similar structure of the transition state, and nonetheless they would never go to the product side, right? Then you can bring the idea is that high resolution structure method to look at that particular composition in detail. So ideally, the strategy would be that you can create a 100 bond-like constraint to lock down this beta term. So upon talking to my organic colleagues, right, they told me that, well, forget about it, right? You can do that using a covalent bond, like a 100 bond, but then you have to change the carbon to some, exotic atoms, which we don't want to do. So, but using that as a guidance, we take one step back. That is, although we cannot create a mimic of 100 bond, but we do know how to link two amino acids together, right? The idea is very simple. Then we just replace the wild type amino acid with two cysteines. Then we can oxidize the side chains to form a disulfide bond. Okay, so of course we can put this constraint at different positions along the chain lines. So our idea again is that this pattern would mimic as a transition state of the folding process of this beta hairpin. Of course, to make the long story short, so we do kinetic measurement for this particular construct. We see now double exponential decays. One actually is much faster, so another one is slower. But nonetheless, this slow component has a value that is quite similar or identical to the relaxation rate of the wild type, which does not have the constraint. So our interpretation, in collaboration with Yiqing Gou's group at Peking University, through molecular dynamics simulation, is that actually the effect of this disulfide cross-link is that you split the population ensemble into two wells. One, of course, both unfolded, but one is that, as our hypothesis suggests, that it contains a folded beta term. So as I told you earlier, so once you populate for the uncross-linked variant at the transition state, it would basically, it's already at the top of the berry, it would fly down through the downhill side of the free-handed berry, generating the folded state. But this one, even you have the cross-linker, but nonetheless the turn is not formed. Then they just do not know the effect of the cross-linker and move on to the folded state as if that there's no cross-linker. So now, of course, you can change these chain lines to change the number of 100 bondings that is required to be zipped up at the downhill side of the free energy berry. And now you can, using the folding time, to plot the folding time against the number of 100 bonds that need to be formed. Okay? So surprisingly, of course, we only have 3 or 4 data points. Okay? So you could choose not believing me, but if you do, actually, you can fit this to this power law function. So this actually is not terribly unfamiliar for those who are interested or familiar with polymer dynamics, right? If you look at a polymer, then you study the end-to-end collisional frequency. So actually, that frequency or that rate would follow this power law. Now, from this exercise, now we can derive or determine the propagation time. Okay? That's a sort of simply a zipping time from the transition state to the folded state. Okay? So as I said before, so when we look at the folding free energy surface, right, due to local corroding effect or non-native interactions. Okay, so the potential energy surfaces would have those sort of roughness. One of the experimental challenges in the field is that how would we do to even begin understand the magnitude of that roughness? Okay, how can we measure that? So again, we don't have good ideas because no matter what experiment you do, you would not necessarily looking at those roughness directly. So what we did here is that sort of naive in the very beginning, and coming back to this triple cage mini protein. So if we put a cross-linker, but in this case, we don't want that cross-linker to change the free energy barrier. But due to the bulkiness of this cross-linker, so upon conformation transition going from the unfolded to the folded, then, for example, those side chains could be bumped into this cross-linker. So as a result, you would amplify the roughness of the energy surface. So that's the idea. Okay, so in collaboration with Bill DeGrado at UC San Francisco, we made this little construct. Then, of course, we do the normal thermodynamic characterization, and also we have done kinetic study. Then now you can see that, so this is the relaxation rate of the free or native form. This is the relaxation rate as a function of a temperature of the cross-link variant. So as we have expected, the overall rate is decreased. Okay, so but that doesn't mean that you necessarily increase the roughness of the potential. You could instantly decrease the folding rate or decrease the unfolding rate. So we have done other works making sure that in this particular case, the introduction of the cross-linker has not really changed the overall barrier, but both the folding rate and unfolding rate become slower. Okay, so the interpretation is that indeed, due to the introduction of the cross-linker, now the inner line free energy surface becomes rougher. Okay, now of course we have to utilize a little bit of theory, and from Zhong and later on amplified by John Straub and Dave Thermoli, because the original theory describing the roughness of the time scale of a particle diffused on a downhill potential, but those guys did was to extend the theory by Zhong for a barrier crossing. So the basic idea is that the roughness in a sort of average sense can be determined by the internal conformational roughness or the friction of the motion along this potential. This one is due to the friction introduced by a solvent. Okay? So by putting all the information together, now finally we can see that at least for this little protein, the roughness introduced due to the cross-linker, which mimic, for example, two tryptophans, is roughly half a kBt. So I don't know if this number is believable or not, but nonetheless, it is a number. So before that, we don't really have a number. Okay. So another story along the line of same discussion is that, of course, we have to consider the frequency of the transition state and the reaction wells. That means is that what is this attempting frequency, right? So for gas phase dynamics, we know pretty well, right? What is the value of these? But for plurifolding, we have been sort of debating actually, how quickly, even for a barrierless transition, the protein would go from unfolded to the folded state. So how can we determine this? So again, this time we obviously lost cross-linker, right? So we used another version of cross-linker, but this one is photoresponsive, right? In collaboration with Andrew Woody, who developed this isobenzene cross-linker. Now, a lot of people have utilized this for a wide variety of applications. The basic idea is that using light, you can toggle this molecule from trans to cis. Okay? So again, coming back to our favorite protein, this is a model system. So we can introduce this cross-linker, and so upon radiation with 355 nanometer light, that you can go from unfolded to a folded state, right? Due to the lines constraint provided by the difference between the trans and the cis. Okay, so I have shown that again the stability of the system has not changed through circular diachronism, and here you are looking at the T-jump induced relaxation kinetics monitored by infrared spectroscopy at a different frequency. So the bottom line is that for the wild type without constraint, without that light, then the system relaxed in a single exponential manner. Now you have obviously two exponentials, right, with light to prepare one of the state. Okay, so the interpretation of the results is the following: that you start from the transform once, then you switch your laser on to populate the cis. So actually, you created a two unfolded state. So one fall to the native state roughly 10 times faster than the other one. Okay, so our interpretation, again, Steve can correct me if I'm wrong, or any theoretist. The idea is that here, again, we did not really change the free energy barrier. So what we did actually to rigidify the transition state, right? Making the tuning the frequency of the transition state. Okay, so that's the idea, because due to the presence of this linker, so the transition state becomes much more rigid. Okay, just like what you would see in small molecule reaction in gas phase, where the entropy is greatly reduced. Okay, so then we can sort of introduce a little mathematic exercise, and using several assumptions. That is, what is the width of your transition state, and so on and so forth. But at the end of the day, what we can do from the data is that to determine the diffusional constant of the particle moving on this energy landscape. Okay, so which is roughly this number, which is not terribly different from that suggested by other people who do simulations. Okay, so I wanted to show you one last story that is a method that I think it is useful. Nonetheless, it's very simple. So as I said, that in order to expose the underlying feature of the folding free energy landscape, right, it is very difficult. You can play many tricks. But one trick which people have not taken advantage of is actually quite simple. That is, since we are doing T-jump, what we can do, just like the people, dentists do this all the time, right? So change the excitation wavelengths, right? Then you can prepare your Frank condensate state at a different place, at the excited state. Here, what we do is that we fix the final temperature. We vary the initial temperature, right? So I guess the students are very smart of creating sort of acronyms. We call it VIP T-jump, basically very initial potential temperature jump. So the idea is that if you have, for example, a downhill-like process which does not include a barrier for the folding, then of course the motion is all diffusive. Then you can see that you would have a relaxation kinetics that depends on the initial temperature. But of course, for two state, so when you change the initial temperature, you only change the population. You would not change the underlying kinetics. So we have done, of course, exercises on sort of systems, beta hairpin. Again, we know that if in a two-cylinder manner, of course, you change the initial temperature, you fix the final temperature. So within our signal-to-noise ratio, they relaxed with the same time scale. For BBL, which Victor Munoz has suggested that this is a downhill folder. Another way of seeing it is there's not a major barrier separating the folded and unfolded. Now you can see that the relaxation indeed depends on the final temperature. But of course, we can do a simple-minded long-term dynamic simulation using that again to determine the diffusional constant of the particle moving on this underlying free energy landscape. Okay, so again, I want to relate back to one of the work done by our friend our mentor, the great scientist Ahmed Zewail. So he has tried very hard to understand the folding mechanism according to their language is the hydrogen atom in biology, that is alpha helix. Okay? So again, we utilize our VIP T-form. So here is the cartoon illustrating the method. Just because you are dealing with ensembles, since this is alpha helical structure, so at any given temperature, you would have not necessarily just unfolded and folded, you have everything in between. So by changing the initial temperature, actually you would position yourself starting from a different ensemble, right? But of course, the final product is exactly the same, but then nonetheless, those time scales would be different as illustrated by the experimental results, right? Using that, of course, we can, because it gives us more information, because you can change consecutively the initial temperature for the same system, you get much more information. Then you can map on all the data to a one-dimensional Ising model, right? Which, of course, involves nucleation and propagation, right? There are many, many states, but now with the power of the computer, we can solve the large number of different equations, and at the end of the day, can tell you that for aniline-based peptide, the so-called nucleation time, which corresponded to the consolidation of really the first hydrogen bond in the helical structure, is roughly 300 nanoseconds, and the propagation time is much, much faster. Okay? So with that, I want to, of course, thank the student who did all the work. As I mentioned that, I would like to thank my collaborators and also the funding sources. Again, I want to thank the opportunity. Thanks you guys for listening. Thank you.
Question, please.
Just one short question, maybe comment to sir about the numbers you shared. You said this is a number. Remember one gamma. And is it not related to entropy? Maybe Casey Hines can tell us something about
No,
it.
this is the friction.
It's friction. It's not a number, just a number. Okay, it's just friction.
Yeah. Oh, thank you.
I don't
I don't think I need a microphone. I just had a question on the trip gauge. So you were talking about the transition state there.
Yeah, go ahead. Yeah,
go ahead.
For the interest of time, yeah.
Sorry.
Go ahead.
Maybe you can ask us then.
Sure, yeah. On the trip gauge, what do you think the nature of the transition state is? So if you define that as like the ensemble that's just as likely to go to one structure or the other, like, what does that look like for that small
Yeah, for the trip cage, based upon our data and also the simulation from our collaborators, the single helix is formed, but the hydrophobic core is not.
My question has to do with the rate analysis. The first underlying assumption that everything is diffusion controlled.
Mm-hmm.
I have no reason to doubt this, but I wonder if it's ever tested.
No, I don't think so.
In particular, I wasn't clear whether you could determine the barrier frequency from your analysis or not. You could imagine that there could be a problem if the barrier frequency is too high.
Yeah, exactly.
So
right.
what are your comments on the testing or lack of testing of the diffusion picture in the first place?
Yeah, I mean, that's a very good suggestion. I mean, for those who have not heard, is that the same piece of data could be interpreted by a different assumption or hypothesis, right? So the frequency of the barrier could be very high or very small. So we did this work actually a few years back, right? Again, the reason that I choose to talk about just the relationship with Zewil's work. But I mean, I don't want to turn this into a political debate, but now in order to do fundamental studies of this nature, at least in the US, it's getting harder and harder. So I still think that even in this field, there are many fundamental questions that need to be addressed, although many of our friends have claimed that we have already solved the protein folding problem, right? Depending how you look at it, maybe we have, maybe we have not. But yeah, we're the very few labs who are still interested in this type of problem. Yeah, we're constantly thinking of new strategies to test hypothesis, for example, ones suggested by you.
Okay, thank you.
Well, thanks a lot. So first of all, let me apologize ahead of time. I'll probably cough a fair amount. I'm getting over an infinitely long cold. I'll also thank Dongping and all the other organizers for this wonderful event and for allowing me to come visit Singapore, where I've never been before. So this is a wonderful time. I'm also one of the few people here who has no professional connection to Ahmed Zewail, but I do have a bit of a personal connection. And it goes back to 1980, which for the vast majority of the people in this room, they probably weren't even born yet. I was a senior in college, and I was trying to decide where to go to graduate school. And I visited Caltech, and my connection to Ahmed is actually beer. So I was sitting and talking with both Ahmed and Rudy Marcus, and they decided that the best way to continue this conversation was to go to the Athenaeum and have some beer. And we sat there for probably the next 2 hours consuming rather large quantities of beer and discussing life and science and all the other things that beer causes you to discuss. But the critical point here was, I really want to paint the picture. I was a 20-year-old college senior. The official title for a person like that is a pisher. I was a rather unimportant person, and these two guys who were about to win Nobel Prizes spent a couple of hours sitting and drinking beer with me. And if anyone gave me a model of how to deal with junior colleagues, it would be Ahmed and Rudy on that night. Okay, so this is my group. I will run out of time. Two of the people are actually here today. So I'm going to talk a little bit in my talk about the work that Shi Chen has done on the things I'm talking about. We do a lot of things in my group. Also, Charles Luft is here, and he's done work on things that are completely unrelated to what I'm going to talk about. And I would urge everyone to go take a quick look at their posters outside when you get a chance. Some of the work today is done in collaboration with a wonderful experimentalist, Professor Vern Schramm in New York. And I'll tell you all about that. And this has all been paid for by NIH and NSF. So as people were describing the way Ahmed went about doing his work, everything he did was to try and answer a big question. And I'd like to think that in some small way I'm trying to do the same sort of thing. So what is my big question? My big question is, how do enzymes work? And it seems rather remarkable that people are still asking this question after something on the order of probably at least 75 years of detailed investigation of this. But remarkably enough, there's still a lot about this process that is unknown. And in particular, the actual way in which enzymes speed reactions is rather opaque to the world right now. One classical example that's given on how they work is so-called stabilization of the transition state. And I don't have time to get into talking about how en face that is such an absolutely absurd idea that it couldn't possibly be right. But there's actually experimental evidence that it's not right. And that is that experimentalists have tried to create artificial enzymes that are designed to do exactly this, stabilize transition states, and they barely work. So the bottom line is a decent enzyme, a mediocre enzyme, speeds reactions by a factor of something on the order of 10 to the 14th to 10 to the 17th. These artificial enzymes speed reactions by something on the order of 10 to the 5th to 10 to the 6th. So obviously there's some crucial design element that people have been missing in trying to understand how these enzymes work, because if they were, they wouldn't be off by 12 orders of magnitude in the rate acceleration. So the question that we try to address in my group is, what is that design element that's missing? So this is a picture of an enzyme. It's to demonstrate to everyone in the room that enzymes are both beautiful and colorful. In particular, this is purine nucleoside phosphorylase. I'll talk more about that later on. But there's a point to actually showing this enzyme, and that is this is a homotrimer, and only one active site is filled at a time. In fact, this is the active site with the substrate bound. And the question that we ask when we look at something like this is, why did nature go and make this glorious design if the actual catalytic center is right there? You would never see an inorganic catalyst that had this much stuff built around it in order to make this happen. So the concept is that in some sense the stuff must be doing something. And the question is, what is the stuff doing? And that's what we're going to try and answer here today. Realize that each one of these amino acids took ATP to synthesize or to break apart from the food that you ate, and it took ATP to hook them all together to make this beautiful structure. So the question is, why is nature doing that? So we want to use theoretical methods to study chemical reactions in enzymes, but there are a number of problems with doing this. The first is that chemistry in an enzyme is a rare event. As I'm going to show you, the actual time scale for chemistry to happen in an enzyme is on the order of femtoseconds. That's why I'm standing here talking to a conference in memory of Ahmed Zewail. On the other hand, enzymes only turn over, in other words, spit out products on the order of every millisecond. So if you used a theoretical method whereby you poised an enzyme with the substrate bound at an active site, turned on the computer and came back and waited to see when an actual chemical reaction happened, you'd be waiting the lifetime of the universe. And that's not an effective use of a graduate student's time. So you need something better than that. The problem is that most of the methods that have existed up until now to study these kinds of systems are various ways that bias the outcome. And there have been thousands of papers written in the literature in which people used various methods to assure that a system went from some stable state A to some stable state B in a finite amount of time, and then express amazement that in fact it went from stable state A to stable state B. What you really would like is an unbiased method to do that. The other problem is that not only do you need to study one event, but remember, enzymes, proteins in general, are sort of soft matter, as we saw from Feng's talk. They're really very dynamic, and they move around all the time. So even if you manage by hook or by crook to find one path that got you from A to B, what you really need is an entire statistical ensemble of paths that get you from A to B. And so if one path was lifetime of the universe, this is lifetime of the universe to the 10 to the 23rd power. So that's a really big problem. So we use a method called transition path sampling. Its origins are actually very, very old. It was repopularized by David Chandler, who we also lost in the last year or so. So the idea behind transition path sampling is it's a Monte Carlo walk in trajectory space rather than the more common Monte Carlo walks that everyone is familiar with in, say, configuration space. It's unbiased in the sense that once you have an initial path that gets you from A to B, and you can get that path by hook or by crook, it doesn't really matter how you get it. And what I'm now doing is sweeping a huge amount of dirt under the rug, because that, in fact, is probably the hardest problem with all of this. The algorithm is designed such that you create an unbiased ensemble from that path of all of the other possible ways, depending on how long you actually run your calculation, to get through phase space from A to B. So there are a number of big advantages to this path, to this method. So the first is that the actual ensemble of paths that you create, like any Monte Carlo method, is determined by, by the acceptance criterion that you use. So as long as you use a correct acceptance criterion, you'll generate a rigorous statistical mechanical ensemble. So as an example, if you use a canonical metropolis acceptance criterion, you'll generate a canonical ensemble. The reason that matters is if you use these paths to actually compute values of any kind, as an example, say, of free energy, it, by the laws of statistical mechanics, should be the same as the actual measurable experimental free energy that you would find in a laboratory. The other advantage to this is that once you have these hundreds of paths, and I'm going to talk about this, we've developed ways that you can analyze them to get the so-called reaction coordinate. And you heard a lot about this in Casey's talk the other day. Unfortunately, the reaction coordinate that many chemists, and especially biochemists, isolate in their textbooks and in their papers are rarely actually the reaction coordinate of the physical system. So as an example, in Casey's talk, the reaction coordinate was not necessarily the motion of the protons, it was the reorganization of the solvent around them. And that's going to be a theme that goes on throughout this talk, that we are locating reaction coordinates, and the reaction coordinates are actually far more complicated than you might see in a biochemistry textbook, And that's the reason, by the way, I'm giving you the punchline at the beginning of the talk, not the end. That's the reason, by the way, that all of these artificial enzymes have worked so poorly. So the first example I'm going to give you is the first actual case we studied. It's an enzyme called lactate dehydrogenase. It's a very ancient metabolic enzyme. What it does really doesn't matter. It ends up transferring a hydride from something that's called a cofactor, which is also called a vitamin, from this NADH molecule, from there to that carbon atom of the lactate, and it also transfers a proton from an amino acid at the active site. So just as a preview, if you were reading a biochemistry textbook, you would be told that the reaction coordinate was the distance of this hydride from that carbon and this proton from that oxygen. Okay? So we went ahead and we did this business of running this transition path sampling algorithm and generating hundreds of trajectories, actually thousands of trajectories. The problem is those thousands of trajectories are just millions and millions of numbers in a computer, and you don't really know anything especially useful yet. So you need to go through a bunch of further steps in order to analyze that data, in order to figure out the real physics of what's going on. So the first step is identifying the so-called separatrix, or the transition state ensemble. And the idea of this is the following. Each and every trajectory is going to have a different physical transition state. There isn't just one single point. And what we'd like to do is we'd like to define this transition state via a rigorous statistical prescription rather than some ad hoc decision about, say, the topology of free energy space, or even worse, the topology of a potential energy space. And the idea is this. This is something called a committer. It goes from reactants to products, and what you're watching here is, if you imagine at each point along the trajectory, stopping the trajectory and reinitiating it with random momenta in every degree of freedom, when you're in the reactant well, the chance of turning into products is very small. That's what I meant when I said you had a rare event. Same thing if you're in the product well, but at some point in the middle, you start to build in probability of going either forward to products or backward to reactants when you do this stopping and restarting thing. And at this midpoint, the 50-50 point, that's what we identify for each trajectory as the actual transition state. And the idea behind this is, if you could do this for all of the trajectories that you've calculated, you would be much closer to finding the actual reaction coordinate. And the reason for that, in turn, is the reaction coordinate is motion that is orthogonal to perpendicular to motion along that stochastic separatrix. And I'll show you a little picture here. So if you remember back to your childhood when you were studying the H plus H2 reaction, this is the Porter-Karplus potential surface. This is a low-dimensional system, so the potential energy and free energy really are the same thing. This is a gas phase reaction. If we did this 1,000,000 times, we ran this transition path sampling 1,000,000 times and calculated the separatrix, in other words, the collection of all points that had that 50-50 probability of going backward or forward, you would in fact find this green line. The reaction coordinate, as you can see, is this purple line, which is orthogonal to the green line. Okay? There actually is a better mathematical definition of that, and that is, if you want to guess what the actual reaction coordinate is, you poise yourself on this separatrix, and you hold what you consider the reaction coordinate to be fixed. And what that will do, and then you run classical trajectories with those degrees of freedom held fixed. And that will cause you to just walk back and forth along the separatrix. If you've chosen the reaction coordinate correctly, then you will continue to stay on this separatrix. And if you now relax those constraints and reinitiate trajectories, you should still get a probability distribution which is strongly peaked about 1/2 to go forward to products or backward to reactants. So this is a way of testing whether your assumption about a reaction coordinate is in fact correct. Now, it's really easy to see how to do this on a two-dimensional potential energy surface. The problem is proteins are not two-dimensional. They tend to be of the tens to hundreds of thousands of dimensions. But the equally important advantage to this algorithm is it doesn't care. It takes longer in a computer, but you still can do that. So you need to, again, identify this hypersurface, decide what you think the reaction coordinate is, and then test it. So if we do that for the lactate dehydrogenase case, and if you read a biochemistry textbook, what they would tell you is that the reaction coordinate was the motion of the proton and the hydride. If you hold those fixed along the separatrix, walk along and reinitiate trajectories, you get probability distributions that look like this, which don't look like they're peaked about 1/2 at all. So what that means in our language is we have incorrectly identified the reaction coordinate. The analogy to what you heard yesterday from Casey is if we had done the same thing for the water hydrogen bond movement, this would have been identifying the hydrogens as the reaction coordinate. Okay? Same thing. In a proton transfer reaction in solution, which is something that has been very important in femtosecond chemistry studies, this would be the equivalent to identifying the position of the hydrogen. And as people like Casey have told us for a very long time, that's not the reaction coordinate. The reaction coordinate, in fact, is the reorganization of the solvent molecules around the reaction coordinate. So what is the analogy in this enzyme system? Well, in fact, it turns out you have to include motion of the protein. And this was something we didn't just guess. We had been studying this reaction for quite some time. This motion of the protein is one that stretches from one end of the protein to the other. It involves all of these amino acids compressing a donor and acceptor across the active site, and it's actually on a picosecond timescale, sub-picosecond timescale, on the order of about 100 femtoseconds. And that's the reason why we're sitting here today. And you know, one of the pleasures for me in coming to a meeting like this is I don't have to convince anyone in this room that femtoseconds matter. You should watch the way this talk goes when I give it to a bunch of biochemists. They don't know what a femtosecond is. They don't want to know what a femtosecond is. So this is something that we called some time ago promoting vibration. The analogy, the first way that we studied it was in crystals of benzoic acid, and they involve the transfer of a proton from one hydroxyl group to the other ionized hydroxyl group. And the idea is when these oxygens get closer together, the diabatic potential surfaces approach each other, and if you diagonalize them to get the adiabatic potential, in fact, the barrier goes down. And I didn't do a very good job of drawing this, but apologies for that. But if you look carefully here, you can actually see that this barrier is lower than this barrier, in addition to being skinnier. Okay? So this is what the idea here is. This certainly exists in the non-biological world. The question is, and that's the focus of this talk, can we identify this in the biological world as well? Is this a mechanism by which enzymes work? So the next enzyme we looked at is a close friend of lactate dehydrogenase. For anyone who had a beer or a glass of wine last night, you're very grateful that this exists. It's alcohol dehydrogenase. By the way, all mammals have alcohol dehydrogenase. God only knows why a camel needs alcohol dehydrogenase. They don't tend to drink a lot of beer, but such is life. They do have it. If you look at the crystal structure, at the donor-acceptor distance, again, we have that hydride to move from a donor to acceptor. The crystal structure has the donor and acceptor 3.8 angstroms apart. If you do what I just told you and watch that distance as a function of reaction along a reactive trajectory, you see a compression and a relaxation. Invariably, the transfer actually happens at the minimum distance, and it turns out that it's about 2.8 angstroms on average. So this has moved about an angstrom from the crystal structure distance in order to get this to happen. If you actually, as I said to you before, we can generate from these ensembles of trajectories, we can generate free energy barriers just from the definition of reversible work. And if we generate the free energy barrier to this, in fact, it's less than a kilocalorie per mole. So what would normally be considered the breaking and making of a chemical bond, because that's really what's going on here. It is truly the breaking and making of a chemical bond, has become essentially a barrierless process, which is kind of an extraordinary thing. The distances that are explored in just 500 femtoseconds over the course of this trajectory is almost 2 angstroms, which is something that biologists will never believe. No matter how many movies you show them, they will not believe this, but yet this is actually what happens. If you restrain that distance to something on the order of 3.5 angstroms, the barrier is 30 kilocalories per mole. So what this overwhelmingly demonstrates is that this is the actual mechanism by which this enzyme actually catalyzes the reaction. the physical motion of the donor and acceptor closer to each other. And of course, this is exactly the way you get reaction in, as an example, a proton transfer reaction in solution. Casey showed this a very long time ago. I guess phenol to amine, proton transfer and phenol to amine. This is exactly what happens. The reason the enzyme does this kind of thing so well is it has everything oriented, and this promoting vibration exists along a specific axis, and I'm going to say more about that in a minute. So this was the publicity picture for Journal of Physical Chemistry letters that we showed. Again, if you just broke the carbon-hydrogen bond that you have to break here, it would cost you 100 kilocalories per mole. That would take the lifetime of the universe, and none of us would be drinking any beer last night. By compressing this distance, this donor-acceptor distance, you get down to about 1 kilocalorie per mole, and that's why you can drink the beer and not keel over. Okay, so the next question is, you could imagine that the protein is like a solvent, like a glass of water. It has vibrations in every possible direction, and just every once in a while there is a stochastic vibration in the direction you want it, and that's what this so-called promoting vibration is, this stochastic compression. So that could be true, but it would also be kind of boring. The other possibility is that this was actually an orientation in the protein that was chosen by nature to cause the thermal energy to actually be transmitted to the inside. And remarkably enough, that's what we saw. The way we did it was, and this was some years ago, we basically blew up a bomb in the center, a computational bomb, in the center of the protein, and we watched the thermal energy equilibrate out to the outside. And in every case, in concentric spheres around the outside of that active site, the residues along the promoting vibration were actually hotter than all of the other residues in that sphere, which shows that this was actually chosen. In results that I'm not showing, we also calculated the dynamic structure factor, and the dynamic structure factor along this general axis shows a long-lived motion, if you will, essentially showing that the protein, again, this is not especially rigorous, the protein is mushier in this direction than it is in all the other directions, and this is in fact a preferred direction for the transmission of this heat. Okay, so the question is, if this is a something that sits in the evolutionary toolbox. How am I doing on time, by the way? If this is something that sits in the evolutionary toolbox, can we watch it actually build in over evolutionary time? Great. 20? 10 minutes, okay. 20? And so the answer is sort of. We've looked, as an example, at two enzymes that exist in nature, dihydrofolate reductase. It does basically the same kind of chemistry. There's all sorts of medical reasons why DHFR is important, but it doesn't matter here. It turns out that dihydrofolate reductase from a bacterium does not have it, but you and I all have dihydrofolate reductase in us, and we do have it. So this is something that was built in by nature in the more advanced, if you consider us more advanced than a bacterium, this is something that was built in by nature in the more advanced organism. Other work in my group has looked at things that are slightly closer in evolutionary structure than a bacterium and a human, and we see the same kind of thing, this sort of thing building in. So we wanted a, in some sense, more rapid test of this, and this is the work of Shi Chen that I urge you to go take a look at. There have been some artificial enzymes created, and as I said to you, they don't work especially well, but they do kind of work. And they've been built by originally computer design, but then laboratory evolution. And the plus that we had was that along this course of laboratory evolution, in fact, they had taken crystal structures of each of the intermediate laboratory evolved states. And so we could use that to do exactly the kind of work that I'm telling you about. This is a chemical reaction, the so-called Kemp elimination reaction, that does not exist in any biological system. So this is a purely artificial, enzymatically, artificial enzyme catalyzed reaction. And the question was, as the enzyme was made more proficient, could we see evidence of this kind of motion building in? And I'm not going to go through this in detail. These are and go to CG's poster, these are these committer distribution plots, and the answer is yes. If you look at, these are the least evolved, this is the most evolved. These look more or less the same. This is a little bit more skewed to the left as opposed to this. And on this side, we put protein motion in this side, we have no protein motion. So it's a little hard to see, but it's in fact there. Now, one of the reasons this is such a poor enzyme is that there is not a huge amount of protein motion allowed. The way they actually build these things is by sticking a catalytic center inside a very rigid outer shell. And if that were not so rigid, then we are sure that there would be more motion. And that's probably one of the reasons these enzymes work so poorly. Okay, so now I'm going to get back to PNP because this is, in some sense, the most exciting work. This is a collaboration between myself and Vern Schramm. We wanted to see if we could take these proposals and actually test them in the laboratory. So the first thing that we did was we wanted to see if the chemical reaction catalyzed by this reaction is the same as that happens in a test tube, because this happens in a test tube just incredibly slowly. So in a test tube, this is an SN2 reaction in which phosphate is the attacking nucleophile, and that's the most chemistry that you will hear from me over probably the rest of my life. It turns out that that's not actually the way the enzyme works. In fact, the phosphate doesn't get anywhere near its final bonding partner until after this so-called glycosidic bond has broken. And the way the glycosidic bond breaks is by a compression of this oxygen with that oxygen polarizing that glycosidic bond. So a completely different mechanism in the enzyme than in the solution phase chemistry. So Schramm's idea, which was a lovely idea, was if you changed all of the atoms in the protein, not in the substrate, but in the protein, so that they were heavy isotopic analogs, you would not change the potential energy surface that you were exploring, but you change all of the frequencies. So if the frequency of this so-called promoting vibration mattered, that should affect the rate of reaction. Luckily enough, and this is biochemistry stuff we won't get into, the indicators of slow motions in the protein were unaffected. The indicators of transition state structure were unaffected, so anyone who tells you that it's transition state stabilization must be wrong, but yet the on-enzyme chemistry went down by a factor of 30%. So what was the reason for this? And we've stared at these kind of pictures for a long time. The red and the black in each case is the actual bond making and bond breaking in this enzyme. But what I want you to focus on is the green line. That's the compression of those oxygens. And you will see in the native so-called light wild-type enzyme, the compression happens just before you reach this pink line, which is the transition state defined by our 50-50% definition in our trajectories. In the heavy enzyme, it doesn't minimize until well after the transition state. And so you still can have chemistry happen, it's just significantly less efficient. So the question that we asked ourselves was, if we've screwed up the timing of this specific compression, could we imagine modulating the protein so we could fix this? Because if we could do that, that would to us be a real indication that we had real evidence for this so-called promoting vibration. The answer is we have. It took a couple of shots. Let me tell you about the first shot, because the reason it didn't work is instructive. So this was the first shot. This was work done by a postdoc of mine, Joanna Zoy, with a research professor in my group, Dimitri Antoniou. And the idea was that if this is sort of what this histidine bats up against, if we made it smaller, made it less bulky, then it would have greater freedom of motion, and that greater freedom of motion would more effectively allow it to compress those oxygens. So we did that, and again, don't bother looking at this, that's for something else. This is the wild-type enzyme. This is that compression, happens right at the transition state. This is the heavy enzyme. It happens, the compression happens after the transition state, as I told you. And this was the mutation that we made. And this was both in the light enzyme, this was the heavy enzyme, and in both cases you got minimization right exactly at the transition state. So I figured, oh, this is cool. I better go get my tuxedo. I'm going to Stockholm, next year. Unfortunately, it turns out it was 100 times slower. Well, if we had looked carefully, actually, at the compression, what we would have seen was that even though it compresses at the right time, it doesn't compress to the same level. So this goes to about maybe 2.8 angstroms, and this compression goes to more like 2.5 or 2.6 angstroms. So the next shot was another mutation that we studied in which we thought we might have a better chance at it, and that is we changed a residue in the neighboring side chain. It was a residue that was designed to actually push the histidine, not just give it more room to flap around, but actually push it. And if you look at the trajectories, it looks like we had success here. And in fact, we get both compression and compression to the same level as in the wild type. Okay? Remarkably enough, this is in the heavy enzyme. In the light enzyme, we don't see this. So if our assumption is correct, then what we should see is the heavy enzyme with this mutation should actually be faster than the light enzyme. In other words, as the biochemists call it, an inverse kinetic isotope effect. And in fact, that's exactly what we see. In the normal wild-type enzyme, you see a regular kinetic isotope effect, but in our mutant, we proposed you see an inverse kinetic isotope effect. So that is, as far as we can say, essentially the slam dunk evidence that this mechanism is correct, that it is at least partially compression of that oxygen pair that's actually causing this thing to be catalytic. We screw it up by making the enzyme heavy by mistiming all of these vibrations. Remember, evolution worked with the natural abundance isotopes, not with the heavy isotopes. And we can repair that screw up. In fact, we go a little bit beyond it by putting that mutation in there. So let me just close by giving you another view of everything. Many of you might know of another Nobel laureate at USC by the name of Arya Warshel. And Arya is a very smart guy, but he has a very different view of the world than I do. His view of the world is that everything is static and that the catalytic effect is caused by electrostatic forces at the transition state. And there is some experimental evidence to show that there's some reality there. So Steve Boxer has done these beautiful Stark effect spectroscopy experiments in which he shows that at least with a bound transition state mimic, he actually sees rather high electric fields at the active site. By the way, Steve instructed me to tell everyone he gives his greatest regrets for not being here. He was already committed to going to Italy this week. But anyway, he wishes he could be here with all of us. So the question was, could we see something as a result of these promoting vibrations that relates to electric field? Because remember, I told you that that oxygen compression, in my language, worked by polarizing a bond. Another way of saying that in Steve's language is it changed the electrostatic environment. So we went ahead and did these calculations, and the very first case we studied was lactate dehydrogenase, our old friend, which was the first enzyme we worked with. We studied the electric field at this carbonyl. That's exactly the way Steve does his experiments. He studies the effects on the vibrational frequency of a carbonyl in the transition state analog at the transition state. And these are just two separate trajectories. And what you can see is as we get this promoting vibration compression, in fact, you see a modulation of the electric field by something on the order of about 30%. So yes, there is a strong static electric field. There are a lot of charged residues just sitting in the active site. But in fact, another way of looking at this is that promoting vibration, in addition to the quantum effect of moving those two diabatic surfaces together, actually also modulates that electric field at the active site. So back to pure nucleoside phosphorylase, we look at this carbonyl. In fact, this is the bond we're breaking. So this is pretty far from this oxygen compression, but we see here a very strong effect as well, that as the compression happens, this is the compression, this carbonyl feels a rather strong increase in the electric field. So what we're basically saying here is there is some synchronicity, if you will, between this electrostatic view and our dynamic view, and maybe everyone's right. One of those rare cases. So these are the conclusions. I don't have to read them, and the chairman is standing up. I think the important point to note here is that these enzymes work because of these sub-picosecond on the order of 100 femtosecond motions. And that now is seeming really fairly unequivocal. You know, science moves on. When I first proposed this, people thought it was all complete and total bullshit. Now we're at the stage where other people are saying they thought of it first. So, you know, you're getting somewhere with this. I think that this provides us with a possible route to actually designing artificial enzymes that will actually work. This could well be at least one of them. I'm not claiming it's the only, but at least one of the factors that have been missing in this enzyme design principle. And that's something that we're going to be working on going forward. It's been a great honor to be here to remember Ahmed and to be with all of you. Thank you.
I think you mentioned that for THFR that the human one has vibration, but the E. coli one doesn't. Does the E. coli one work as well as the human one?
That's a great question. So it's a question of how you define as well. So there is a problem, and that is that in almost no enzymes is the rate of chemistry actually the rate-limiting step. And in fact, in almost all enzymes, the rate-limiting step is release of the product. In fact, the human enzyme is a little bit faster in that. No one has actually measured the actual rate of chemistry. That's a very hard experiment to do. It's called an on-enzyme chemistry experiment. My friend Schramm does it. Not many people actually do that. So that was a long answer to say I can't tell you, and we don't know. There is a real philosophical question about this, by the way. Usually, the actual rate of chemistry is many, many orders of magnitude higher than the rate of product release. And so one question that you can ask is, why has evolution maintained that over billions of years? That's something to discuss over beer. And I think we have some answers for it, but it's certainly not proven.
Thanks, Steve. I don't disagree with much of what you said, but
that always is a bad sign when someone says that.
well, I did insert a but. I think it's very useful in these discussions to be quite clear about terms.
Mm-hmm.
And I think a lot of heat-generating confusion is related to the use of the word dynamics.
Totally agree.
Okay. One definition of dynamics in connection with a reaction would be, does the chemical reaction depend upon the rate of a particular process? That's certainly. So, for example, we heard this morning about a diffusion control reaction. The rate depends upon the diffusion constant. It's diffusion control. So let's go back to your example where the energy was flowing into some particular coordinate. I would ask the question, suppose you look at the rate constant for the reaction where you've got a flow in the reverse direction, or in any of these other examples, I have to have a certain compression or a certain dilation or whatever. Does the rate constant depend upon the rate of that process? That is one definition
And
of
that
dynamical. And I can
Okay.
still have something that one would call a promoting mode, and many people use this language, where that mode is absolutely key. If you didn't have it, the reaction wouldn't occur at all. But in the actual reaction, what counts is the probability of compressing or whatever, but not the rate of energy flow.
Yeah,
See what
so
I'm talking about?
I do, and I think I agree with most of what you just said. And the answer is, in some sense, that's exactly what the Schramm's, as he calls them, it's a wonderful name, the Born-Oppenheimer enzyme, what Schramm's Born-Oppenheimer enzyme does. When he changes the mass of all of those particles, he changes the rate of the compression of the important mode. Now,
I don't agree with that.
well, we can discuss that.
Well, the equilibrium probability of these compressions depends upon the entropy,
So
which depends upon the
the
mass.
problem here, the problem is, and this is where we are in complete agreement, you imagine that this protein has these gazillions of vibrations in it. Other things have to happen for the reaction to occur. The reason that this slows it down is that there is no longer synchrony between all of those other things and this specific motion, or it finds, in your language, it finds that the probability of finding that synchronous state has gone down significantly. So in many ways, these are different ways, different pictures of looking at the same kind of thing.
Well, we could continue, but let's continue elsewhere.
Sure, fine.
I mean, you have two events. How is the phase maintained?
I'm sorry, how is what maintained?
The timing, the phase.
You mean in a real enzyme?
Yeah.
So the answer is, it's usually not. And that's one of the reasons why when it actually happens, it takes only a femtosecond to happen, but the rate of chemistry, even the rate of chemistry, not the rate of turnover, but the rate of chemistry is much lower than 1 over a femtosecond. It's because a lot of other stuff has to happen. The phase doesn't get maintained. And that's exactly speaking to what Casey was saying.
First off, I'd like to thank Dongping for inviting me to this great symposium. It's been I've been learning a lot. And, I hope to kind of keep the discussion going. So what I'm going to talk about is something that I've been working on for a while. I put it on archive a little while back, and I'm just about submitting it right now. So any kind of feedback on the kind of the semi-final version would be appreciated. So all of this got started. During my PhD with Ahmed Zewail. So when we started on this journey, the kind of framing of the whole problem is kind of encapsulated by this paragraph in a review article we wrote at the end of my PhD. Right? So basically, starting at the organism level and magnifying to the organ, cellular, and macromolecular scales, the length scale of biological complexity spans 9 orders of magnitude. In conjunction, the time scale of biological dynamics ranges over 22 orders of magnitude. But life maintains both complexity and robustness, which is defined as structural and functional reproducibility over these vast length and time scales. So that's amazing. Right? And in characteristic AZ fashion, the question that he started me down, and the one that I'm still working on and I hope to work on for the rest of my life, is a very simple one. Right? So, are there simple and general laws for life? And in order to really answer this question, we need to find or to build the tools to answer this question. So, I would say aside from protein folding and aggregation, most of the processes, biological processes at the macromolecular scale, at the building block scale, happens out of equilibrium, right? So, processes that have to do with signaling, having to do with building and destroying infrastructure, having to do with transport, having to do with replication. And all of these processes are driven actually quite far from equilibrium, and they consume energy and they dissipate heat. However, non-equilibrium behavior itself is poorly understood, right? So we would like, going back to AZ's question, we'd like to be able to have answers to really simple questions like, what is, given the system, what is possible and what is not possible? What are the limits of performance of the system? And if you want to get to those limits, what are the costs, right? In energy consumption, in efficiency, and speed. Are there, for these biological systems which are heterogeneous but still have many, many degrees of freedom, is there a systematic way to coarse grain the system so that into the really important collective variables, right? So that we don't have to worry about all the actual microscopic degrees of freedom, right? These are very simple questions which, out of equilibrium, have challenging answers. Okay, so to define what that means a little bit more rigorously, let's just go back to what is known very well, right? Which is the equilibrium, which is a form of steady state in which there is detailed balance, right? So it's a special kind of steady state in which between any two states of a system, so here's a node that will be a state of some system, here's another state of a system. At equilibrium, the forward transition between this state and that state is exactly balanced by the reverse transition. Right? So and the probability then between any two states, even very far removed in state space, is given by the Boltzmann distribution. Right? So if you know the free energy difference between these two states, you would know their relative probabilities. And of course, there's no net current anywhere. Okay. What's important to know is that this is really powerful because this defines a relationship between local and global properties of the system, right? So this GI is a local property only of the state I, and same with the GJ, it's a local property of state J, and yet this Boltzmann relation gives you a relationship between what should, in principle, be global properties, which are the relative probabilities, right? Because every state is connected to every other state. But at equilibrium, you can just get the global property from local property. That's why it's so useful. But out of equilibrium, that no longer holds, right? So you can have other kinds of steady states, right? In which now you can have net currents. And so therefore, for example, in this particular cartoon, even though it's a steady state so that all outward flow from a state is equal to the inward flow, you don't have detail balance so that you can still have like current loops, right? And those current loops have to be driven, and they can, in principle, do useful work. So the question here is, in order to really answer this initial question, right, set off by Professor Zewail, their simple laws of life, we really need to have something akin to the Boltzmann distribution in which there is a relation between local properties and global properties. Otherwise, we're faced with counting the transitions between the exponential number of degrees, exponential number of states accessible to biological systems, right? So that's what this talk is about. So let's start out with a really simple example where you just have a system can only exist in 3 states, okay? So at equilibrium, right, I'm just rewriting the Boltzmann distribution for state 1 versus state 2. You can rewrite this so that it's really writing in terms of the forward flow minus the backward flow between state 1 and state 2, which is by definition a current, and that is 0 at equilibrium. Okay, so this is just another way to write 0 at equilibrium. But if you stay with me for a moment at equilibrium, notice that we can map this constant, which is only a property of equilibrium conditions, right? The free energy and the forward rate constant, to what I'll call a resistance. So the resistance is conjugated to the current, and the resistance is just defined between the state m and n, defined to be e to the beta gm over the rate constant of kmn, okay? And what's important to note about the resistance is that it's symmetric. So the resistance as defined between m and m is the same as that between n and m, okay? And that's because the resistance is really just the reciprocal of the forward rate of transmittance at equilibrium, which is exactly equal to the reverse rate of transmittance at equilibrium. Okay, so, but what makes it interesting is what happens when now you drive your system out of equilibrium. Okay, so it's still the same simple system, but now you start with the equilibrium system, and let's say you drive some rate constant, right? And with an additional rate constant. That could correspond to this particular step having to do with replenishing a supply of fuel, right? Your rate of binding ATP or GTP is suddenly way, way, way higher than it would be at equilibrium. Now you drive the whole system out of equilibrium. So what happens here is that you have an additional term here that has to do with the direct effect of driving this particular rate. But also, now your currents are no longer 0. So to continue the mapping then, I've already defined this part as the resistance, the resistor. I'm going to define this as the battery. And I'm going to define this term to be the potential of a state. Okay, so notice that it's a state function. It's only a property of the state, which the probability of the state basically normalized by its equilibrium probability. That's going to be what I call the potential of a state. Okay, so what's useful about this is that now, with this definition, if you go from any state to any other state, the potential difference is equal to the battery drop, which is the number of things that you number of transitions that you directly drive, right, given by that equation I just told you, minus the resistance times the current along the path. And this is true for an arbitrary number of states in a loop. So it would be useful if this also held for an arbitrary state space in which any state can be connected to any other state anyway, right? And it is. So this relation also holds along any path from any state to any other state. And it holds whether or not you're at equilibrium. You could be at a non-equilibrium steady state, or you could be in a time-varying relaxation from one non-equilibrium state to another. So just a reminder, here's the mapping then. There are passive elements and there are driven elements. Okay, so the generalized Boltzmann distribution is a mapping to a very special kind of electronic circuit in state space. Okay, so the passive elements are the actual voltages at a node, which is this is how you map. This is what the voltages are, and then the resistors, which are a function of only equilibrium constants, and this is how you define the resistors. Okay, and there's the driven elements, which I told you are the battery, which is an energy source, and there can also be a mass source, which corresponds to a ground, okay, electronic ground. That's when a voltage is held constant. Okay? The reason why I say it's peculiar is that unlike most electronic circuits that you may be familiar with, this is the batteries are voltage dependent, right? So remember that the voltage drop is proportional to the actual voltage at this node. So there's inherent feedback to the battery. Other than that, the whole circuit behaves just like a regular electronic circuit. And the most important property is, again, the symmetry and direction of the resistance. That the resistance is the same if you drive it in the forward or the reverse directions. And notice that at equilibrium, all your alphas are 0 because you're not driving any transitions at equilibrium. So your batteries are 0. Your currents must also be 0, otherwise there will be a loop along which there are no batteries, but there's still currents. And you just get back the Boltzmann distribution. So in this mapping at equilibrium, the Boltzmann distribution just corresponds to equal potential circuit. You have a circuit that have no battery, that you're not driving, so every single node is at the same potential. It's pretty boring. Okay, so how do we actually use this to understand biology then? So the reason why this mapping is useful for biology is that biological systems have the properties that they may exist in a large state space, that, for example, a protein complex or a signaling system can exist in many different states, but only a small subset of those states are directly driven, say by ATP or GTP hydrolysis, right? So that means that you have a sparse set of driven transitions in a large sea of undriven transitions. So if you have this then mapping, you can take some non-equilibrium system, right? Here's what it actually looks like microscopically as you're driving it. Here's a transition that you happen to drive out of equilibrium. Here's a mass source. And you can map it to circuit, and then you can simplify the circuits in series and in parallel, just like electronic circuits. So you can have systematic coarse graining into modular degrees of freedom, in which if you're interested in the macroscopic behavior of the system, you don't have any loss of information. Okay? This is really the effective resistance of this entire thing. Okay, so what does that look like for? I'll just give you a couple of examples to see how this would work for particular systems. So here's an example catalysis of just, let's say you want a very simple picture of catalysis where there's just an enzyme and there's just 3 states. It converts products to reactants, and the driven transition is in which you just magically replace the end product with fresh reactant. Here's another example where it's a single loop. Here's this probably the most important signaling system in your body, right? So this is RAS. Basically what it does is it takes upstream signals. Basically these signals come from outside of the cell, and RAS then decides to turn on to activate the response from inside the cell. And so when RAS is bound to GTP, it's on, and all the other states, it's off. So by controlling the population in this on state, you turn on or you can activate the cellular response. Okay, so here it's driven by the replenishment of GTP with fresh GTP. Okay, so that's what, and notice they're both just systems that have loop state topologies. So this is what the circuit would look like for both of those systems, right? So signaling in principle is different from catalysis, but they all are formed, they're all part of this class of circuits where it's just one battery and you're driving a bunch of resistors, okay? For the simple example of catalysis, there was N is 3, there's 3 states, and for the RAS signaling system, there's they have measure 5 different distinct states, N would be 5. But using the general the circuit equation, which is the general Boltzmann distribution, this is what the current and the probabilities of all the states are. Okay. So just as a sanity check for the simple 3-state system, if I just map it to variables that we're all more familiar with, this is what it looks like. So you have this alpha is how far you drive it from equilibrium. Okay, so notice that if you drive it so far from equilibrium that this process is irreversible, you get back the Michaelis-Menten equation as you should. But now this tells you how this would be modified if you actually did not have an irreversible catalytic event. So here's the equation. This is for arbitrary number of states with arbitrary rate constants between, okay? So this is that general equation. Here, I'm just showing a consequence of this, right? And now you have a closed form. A consequence of this is so you can show that the log of how much you want to magnify, so the P star, any stars means that it's the equilibrium probability, okay? The probability before I drive it. So how much I can amplify or de-amplify, like a probability from its equilibrium value, is bounded by the power dissipated divided by the current, which is basically the energy cost per cycle divided by KT. Okay, so no matter how big your system is, and no matter how you finagle the rate constants, you cannot magnify the probability of any state of interest beyond its equilibrium probability if you don't pay this exact upper limit of energetic cost. So that's a fundamental bound for this class of systems. Okay, so here's what it looks like. And this is what it looks like if you plug in the measured rate constants for RAS. Okay, there's basically there's 2 different possibilities. One in which RAS is the on state is promoted by an additional cofactor called SOS, and that's shown in the white dots for the 5 states, 1, 2, 3, 4, 5. And then the black states are, if you don't have SOS, here's 1, 2, 3, 4, 5 states. And this is just showing the magnification from the equilibrium probability. So at equilibrium, the on state is basically 0. Out of equilibrium, in the SOS case, it's about 98%. In the non-SOS case, it's 35%. So in vivo, your body is modulating the on signal from about 30% to about 100% as it switches on and off the response. Okay, some of the states get pretty close to the bound, but you cannot magnify any states beyond the bound if you're paying this much of energy. Okay, here's another example. How much time do I have? Here's Okay, great. Here's an example of self-assembly. So this is a microtubule self-assembly. So microtubules are one of the two classes of cytoskeletal elements that give shape and movement to your cells. Right? So they assemble, and they're driven in their assembly because GTP is bound to the dimer before it adds on. But there's also a pathway of catastrophe in which the cap can break and the entire thing can banana peel back out. Okay. There's also cases where you get rescued, but this is the basic picture of microtubule dynamic stability. So here's the microtubule system mapped to the circuit. And you can also solve this one to closed form solution. Here's the solution. So what's interesting here is that it's actually a superposition of the equilibrium distribution. Delta G is just a free energy change of adding a monomer or adding a dimer of microtubule, plus a non-equilibrium term that's also an exponential decay, but has a decay constant that's dependent on how far you drive it from equilibrium, but now also dependent on the catastrophe rate. Okay. So at equilibrium, it doesn't matter what the catastrophe rate is because rates don't determine probabilities at equilibrium. But not when you're out of equilibrium, you can now have the catastrophe rate determining the actual length distribution of microtubules. Okay, so here's a plot of if you plug the microscopic parameters into the solution. Here's what you get, right? And the color plot tells you how far you drive it out of equilibrium, and this red, this line is at the in vivo levels of driving out of equilibrium, which is the in vivo concentration of GTP. Okay, so basically, if you drive it close to equilibrium, you get almost no effect on what your rate constant of catastrophe is. Okay, but if you drive it sufficiently far from equilibrium, now you have a linear effect on your catastrophe rate. So this is something you can't achieve at equilibrium, right? So this is a rate constant of a process that only affects the end cap of your really long thing. Just affecting the rate constant of that can actually linearly tune the equilibrium, the steady state distribution of the length of your microtubules itself. So you're using a boundary population to control the whole bulk, right? And as expected, when you're at equilibrium, you get a flat line because we know that at equilibrium, the catalyst rate cannot affect the probability distribution. Okay, final example. Here's a process of kinetic proofreading. Okay, so in order to translate your DNA code to your amino acid code to make proteins that does everything in your body, there's a process of translation, right? So you have a ribosome, and here's the codon, right? I'm going to show it as this trident, which is 3 nucleic acids, and that is hooked up to its proper amino acid, right? So what happens is that you can attach, here's the growing protein, right? And here's the rest of the mRNA sequence to be translated to the remainder of the growing protein. So you have another thing that binds, and it binds. This is the correct binding. So the black matches with the black, right? Then it can proceed, and then it can proceed to success, in which it links and adds on a unit to the protein, and it can reset. But it can also fail here, right? And all of these steps are also reversible, so it can also fail here. The reason why this is important, and it's called proofreading, is that there is some probability that you bind the wrong codon and you get the wrong amino acid. You don't want that. This thing will bind with less energetic stability than this thing because there's a mismatch. So there's a higher probability of falling off here and a higher probability of falling off here. Okay. So this is the process of proofreading in which this system has evolved to get high fidelity of getting this and not getting this. Okay. So here's what kinetic proofreading looks like as a circuit. Okay, here's the success and fail, and here's the correct, and here's the erroneous side of the thing. One thing that you can derive from the non-equilibrium Boltzmann distribution of the circuit equation is that you can, I forgot to mention, in all the plots I showed before, all the dots on here were experimental measurements, okay? And all the actual curves were the equations that I showed. So before, the thing to know for the microtubule is that experimentally they measure the microtubule length contracting about a threefold in the 2 phases of the cell cycle by only controlling the rate constant of the catastrophe. Okay, so here, one interesting kind of limit you can get for a proofreading system like this is that the efficiency, the error, right? So one thing to know is that the minimum error is actually the square of the what you would expect to get without proofreading, right? Because e to the negative, so delta is the energy difference between the correct versus incorrect codon binding, right? So you would expect normally you would get e to the negative delta over kt factor of error, because that's the energetic difference between the two. But with proofreading, you get you get that thing squared, okay? But you need to consume energy to get to that limit. And here's the actual trade-off between how much error you get and how much energy you need to expend. So P is the total power expended in the system, and I2 is this current, which is the current of correct processing of adding the amino acid, right? So, and this, the 3 dots are actually the measured inner error versus the catalytic cost for AAA versus AAU errors, okay? And what's interesting to note is that the biological system has evolved to be at the edge of this forbidden zone, right? So it performs, and in fact, by changing the magnesium concentration, the biological system willingly trades energy for error. But it's all along the kind of this forbidden boundary as defined by this equation. Okay, so those are just some examples for different kinds of systems. Here's what can we say about like biological systems in general. Okay, so here's some process where I'm driving it by ATP or GTP hydrolysis, right? And it does something. Okay, there's a lot of states in here. I'll call that the load of this resistor. So there's one effective resistance that corresponds to all the stuff that happens. Okay, and this resistance can be built systematically through the laws of combining resistors. But there's a load resistance which is also called the Thevenin equivalent resistance. Okay, and you can show that the maximum energy efficiency of such a system with arbitrary load resistance is given by this formula. The reason why you can show these general formulas is that you can apply decades worth of advances in the theory of electronic circuits to apply to non-equilibrium systems, and in which they take on very different meanings. Okay, here you can only get this result by applying something called Teligent's theorem for electronic circuits. But the upshot is that the maximum efficiency is only a function of the load resistance and how far you drive it from equilibrium. So this is what it actually looks like. So this is how strong you drive it, and the different colors correspond to different load resistance of different processes you could be driving. Okay, and the thing to note is that monotonically, the efficiency goes to 1 as you drive it far from equilibrium. So this is the isothermal version of the Carnot efficiency, right? So for many years, people are trying to design better and better heat engines, and then they just figured out that you can't exceed the Carnot efficiency, right? Which is determined by how much hotter the high temperature bath is compared with the cold temperature bath. And the reason why our heat engines are so inefficient is because we can't maintain like a 1,000 Kelvin heat bath and then dissipate to like a 100 Kelvin source, right? That's really hard to do unless you're at like a nuclear reactor or something. So that's why the efficiency of our heat engines are really, really bad. But if you're a chemical engine, there's no problem in driving your system really, really far from equilibrium, right? ATP concentrations are like 10 orders of magnitude higher in your body than they would be at equilibrium. And so because of that, because we're driven by chemical engine and not heat engines, all of these processes of our bodies are intrinsically capable of being essentially perfectly efficient. Right? Any loss you have is due to the design of that system. And we're actually, for this particular one, we're testing this experimentally. Right, so we can actually, we're setting up single molecule experiments, and we can directly measure the energy efficiency of kinesin, and then see, as we tune the ATP concentration, whether or not the efficiency matches that of the theoretical condition. Here's my grad student sacrificing sea urchins to get their sperm, to get the microtubule, stable microtubule tracks on which the kinesin can walk. So the final thing, do I have any more time left? 3 minutes, perfect. Okay, so the final thing is the reciprocal relation. So this is also a very general result. Basically, it governs a reciprocal response between driving one part and the response in another. So let's say you have some complicated system, and let's say I'm driving this particular transition, right? And not only will I get a current here, I'll get a current everywhere. In particular, I'll get a current here. Okay. So you can also ask, well, what if I didn't drive this thing? What if I drove the other thing here? What would be my current here? So you can use the Lorentz reciprocity theorem from circuits to show that this is the reciprocal response. That the relative sensitivity of one part to driving in another is just given by the ratio of their load resistances taking at the 2 points. And in particular, that means that for any system, there exists one transition that is the most, in which all other transitions are most susceptible to. Okay, so one of the things that we want to see is whether or not in living systems, they've evolved so that the ATP or binding transition corresponds to that one, right? Because that would be the one in which driving that transition makes all the other ones the most susceptible to. In a special case when you're driving very close to equilibrium, this recovers the Onsager's relation for linear response close to equilibrium. But this relation is valid arbitrarily far from equilibrium. I did have one final example. So here's just an example that because they're electronic circuits, we can ask, can we engineer things just like we do with engineering actual circuits in physical space, like the ways that you can build up circuits to make something like your iPhone or your laptop, right? So here's an example of a system, a very small system in which you can tune, by tuning its resistor, you can tune it to be either a switch bias ultra-sensitive system, so it'll be a switch transistor, or a 2-bit memory because now it's bistable, okay? And this is only possible because you have a mass source. So here's one system in which by tuning it, you can get both a transistor and a 1-bit memory. And in principle, you can make a system that's Turing complete with this. So you can systematically then design circuits with the same laws that we've been using to design actual physical circuits. But these would be for non-equilibrium dynamics in living systems. So I think getting back to the original question that motivated all this, I think we're still in the kind of early stages of both flushing all the examples and as well as experimentally testing as many of these things as possible. But I think we're on the path to answering this question that AZ set out for himself and for me and for other members of the group is, are there simple and general laws for life that apply not just for a particular example of a particular system, well-studied system, but apply for either very general classes of systems or all systems. So with that, I'd like to thank you guys for listening to my blueprint funding sources.
Exactly what you mentioned early on. Is the detail balance maintained or not for the driven system?
For the driven system, detail balance is not maintained. You can have balance in which you have steady states, but you wouldn't have detail balance.
But you still use, I guess, if I remember correct one equation, using the steady state probability, propagated to the answers. Or in other words, that the flux is zero.
Yes. At equilibrium. Yeah.
But you still use that condition.
Let me go back to the. So you're talking about the condition in which I have still the same equation, but now the current is no longer zero. Is that the one you're talking about? Just, alright, let me exit this. Go to this. Alright.
I'm not sure.
So I'm going to go forward, and then just tell me when I should stop. Okay.
So here it's okay, right? So
Yes.
start from
Yes.
steady
Yeah.
state, then you move on to a driven system.
Right. So
Yeah.
so this okay. So far so good, right?
Yeah.
And then you have a problem with now this.
Yeah.
Is that right? Yeah. So turns out that this part, if I go back, this part before the zero, this is just a definition of what the current is. So this is always true, right? So the current is equal to the forward minus the reverse rate fluxes.
But presumably you know Zhong's work. Actually, for a non-equivalent system for dynamics, where even at the current is zero, then you still have a curve, sort of divergent gradient, which contributed to the net flow.
So all of these G's are the free energies at equilibrium.
Yeah, that's the potential, that's the gradient.
Yeah.
But
So
on top of that, you still have a curve force in the system.
I still have a what force? Sorry.
We can talk about that. I mean, from Zhong's work.
So this is just like there's no extra magic here. Okay, so this is just a definition of what the current is. This is just what the definition of the current is. If you cross multiply by both sides, you literally just get like the current flux is equal to the current is equal to the forward minus reverse flux. Now with the alpha, the forward flux has an extra term because you have an extra rate constant. But this is just literally the definition of what the current is. So.
Very interesting work. Congratulations. I have two questions, and I'll say them both. The first is that it seems to me that your analysis only makes the assumption that you have linear rate laws in terms of the probabilities of the states. You agree with that?
Yeah. So.
Okay. So let me ask the second question then.
So let me get back to that point. So that's an important point. So the fact that you can combine resistors in that way does apply on that, because otherwise your resistors will actually be dependent. You just have more exotic resistors. But this equation wouldn't change.
Okay. Yeah. So everything is linear. The second question is, suppose I have an underlying system where the chemical rate laws in terms of the concentrations are nonlinear.
Yes.
What happens then?
Yeah, so this also applies when it's nonlinear.
How do you make them mapping?
Your resistors are no longer constants.
So all the nonlinearity implicit in the chemical rate laws and concentrations gets thrown into the resistance.
Right. So as I said before, the resistance are the most useful when they are linear because you can combine them systematically.
Yeah, right.
But this equation also applies when it's nonlinear. Yeah. In fact, the last example I showed was for a nonlinear resistor, and that's the only way that you can get bistability. You have a bistable system.
Okay, thanks.
With a linear system, the other element and resistor.
Say that again.
Can you make that with other electronic element?
Oh no! If it's nonlinear, you just have nonlinear resistors. I think in the last example I showed, there was one of the resistors is now a voltage-dependent resistor. Yeah.
Thank you. Thanks.